Good?
Yeah.
Okay.
I think that's good. Yeah. I mean, we can always change it during the talk.
So can I just ask you to put like the right image with the splash name?
Yes, yes. We were just testing.
Sorry. Oh, okay. Just checking. Do you find with the audio microphone you want your walking?
No, I just stand here.
Sit there?
Yeah, like it.
But is it fine that I have a walk in the afternoon session? Is it fine if I use the
The handheld. Yeah, you can use a handheld. One thing you should be aware of is that it won't record your video very well if you're not at the perfect spot. If you're okay with that.
So there's no remote for the camera, right?
No, no, we do not.
I was in the other room, and I was in the volunteer, so I was like, follow me.
Yeah.
I will not move that much, but it's fine. It's fine. Just handheld mic, headset,
Yeah.
and me, Elon Musk.
I mean, if you want to move, you definitely can. Like, you won't need any of these things.
I think I'll take the handheld, but I will probably stay there most of the time.
Okay.
Let's see. Not working. No.
There we go.
Can you compile the slides in 4:3 ratio?
To what?
Oh, now we have.
Compile the slides in 4:3.
What do you mean?
This is 16:9. Okay. This is a bit long version, but it's fine.
But if I play it like this,
this is
right?
fine.
Yeah, this will be fine, right?
Is it fine on the
What's that?
on the streaming? Is it streaming? Is it like back ratio or is it
It's streaming right now. If you want to see how it looks on the projector, I mean, this is what it's streaming. I'm not sure. Somebody will be here. Yeah.
I'll leave the microphone open on the right stand, so if anyone wants to make questions, major time, they can go to the
Yeah.
stand. You want to do that other one, customer? Yeah, it's big room. I think there's a lot of people in from customer.
Yeah, it depends on
They cannot move on all
Oh, that is a good point. Yeah, the bigger it is, the harder it is to get to the metal.
Well, but the bigger it is, the longer it takes to deliver.
That is true.
We can have a student one here.
Yeah, somebody will be here that could pass it around. Also, we do have two mics. If the speaker's not using one, we could always like get one to
Yeah, the speaker has the routers.
Yeah. We can use both of these mics,
Yes,
right?
of course.
Yeah.
I was thinking that you wanted one for the moderator, for the.
That is true. That is true. Yeah. Yeah, actually, Michael, you'll probably want one during the podcast. Yeah.
For the opening.
And so then one for
Yeah, usually.
Yes, there will be a number.
Is that they would refer to you?
At least one.
Yeah, I think
What's that? Yeah.
So
Yeah, there should be a volunteer.
I asked the chair if you cannot answer some question and you think that you want to answer it or Suresh to answer it, just tell that he can handle it and then I can answer it. Okay.
You could also decide you're going to go up or you're going to go down. So whatever. So you can do.
So maybe after presentation, stand here or so?
I mean, I will sit here,
Oh,
and
okay.
you can just point toward me if you want me to answer
Okay,
some
okay,
question.
yeah.
I'll stand up and
Contact,
answer it.
yeah,
It's
okay, okay. Perfect.
I like the name Asparagus.
Hmm?
I like the name Asparagus.
Yeah, we used a lot of time to come up with the name.
Does it stand for something?
Hmm?
Does it stand for something? Oh, yes, it does. Alright, I get it, yeah.
Hmm.
But the C doesn't fit.
Yeah, we can have this focus.
Wait, what is on that screen?
The first slide is on the screen.
Oh,
We're
okay.
talking about the Asparagus name.
Yeah, yeah.
But the contract says C.
You can take a smart mark as one word.
Smart contract. So you said you wanted a mic. What order are you in?
No, I'm not right. I'm the afternoon session. Just
Oh, okay.
Okay, welcome everybody. I know people are probably still filtering in, but I want to make sure we allow all the time for all the talk, so I think we should get started. I'm Michael Koblenz. I'm your session chair for today. I'm from UC San Diego. Welcome to our first OOPSLA session on data compression, in which all of our authors compress years of research into a 15-minute talk. Today's topic is program synthesis. Our first paper will be presented by Zhu Kai. It's called Asparagus, Automated Synthesis of Parametric Gas Upper Bounds for Smart Contracts. I'm really excited about all the talks today. Go ahead.
Okay, thank you. Good morning, everyone. I'm Joe. I'm happy to present Asparagus, which is automated synthesis of parametric gas upper bounds for smart contracts. And this is joint work with Suruj, Amir, and Hitas from the Hong Kong University of Science and Technology. And okay, so what is smart contract and gas? So smart contract is just programs that blockchain that all the full nodes should execute. So since everyone has to execute it, then calling the public function of smart contract is not cheap. You need to pay transaction fee, and this is called gas. And it's proportional to computational resource, which is time and space. So people write smart contract in Solidity source code, like the code over there, and then it's compiled to this virtual machine bytecode, which is just a list of opcode. And for each opcode, there's a gas defined on this operation. So the gas usage is just the total gas usage of all the opcodes that you will execute in the real time. And so why is it challenging to estimate the gas bound? So most importantly, because the smart contract programmers just write in Solidity. It's a friendly language, but the gas is assigned to the EVM bytecode, which is really ugly. And when the code size is huge, you have hundreds of lines of Solidity code, then you will have thousands of lines in bytecode. And it's really impossible for a human to estimate how much transaction fee you need for this transaction. So, since gas fees is just proportional to the computational resource, and then smart contract is a Turing complete language, it has all the challenge of resource analysis of just common program analysis, like conditional branches or loops. And note that the actual gas usage is dynamic depending on the blockchain stage when the transaction is actually handled. But we want to have a static bounds, so it to be parameterized by the real-time state. And one more challenge here that for single opcode, we define a gas, and the gas can be non-constant. For example, the SPLASH'23 is just computing the hash of a string. The gas usage is linear with respect to the length of the string. And this makes things a little bit more complicated. And then it can be piecewise constant, such as storage writes a value x to a storage. And it depending on the old value and the new value, the gas can take these three different values. So we just use the largest gas cost to be sound. And so now we can present the overview of Asparagus. We take Solidity smart contract as input. And since gas is defined on the bytecode, we need something to compile it and extract the control flow graph of the bytecode. And since estimating the gas is only decidable if we restrain ourselves to polynomial systems, so we need to do some over-approximation to transform it to polynomial transition systems. And then we formulate our problem by adding just invariants and ranking functions. And finally, we reduce our constraint system by the three theorems from real algebra geometry to efficiently solve everything. So I'm introduce the blue parts, which are sound and semi-complete. So what are the constraints? Suppose we already processed the system into a polynomial transition system, which is a set of locations, a set of variables, and polynomial transition, which means the variable update is polynomial, and the condition is polynomial inequality, and gas usage also polynomial expression. And we define ranking functions, which we call remaining gas polynomials, just ranking functions weighted by gas usage. And we also might need inductive loop invariants. And these are all polynomials on the program variables V. So this was one example about the ranking function at location L1. So like Vinium vote count is the program variable, and these t's are the temporary coefficients that we don't know, but we want to solve. So overall, we will formalize the problem as constraints on the program variable v and the template coefficients t. And the constraints just saying that, okay, you have to satisfy the requirement of ranking function, so at each transition you have enough gas, and then also you satisfy the definition of inductive invariance for those template invariants. And so over the format of the constraint really looks like this. So exists some value for the template coefficient, and that for every possible value of the program variables, as long as some polynomials on these variables are non-active, then some other polynomial is non-active. Then this means the inductive variance hold or ranking function is positive, something like that, and then you have enough gas, and then the variant hold after the transition. So if we can solve this constraint system, that basically means we can get a solution for this T. Then this basically means we have a valid gas upper bound. So now the problem is to solve it. And recall that we have this format of constraints, and our goal is to find a valid solution for template variables T. But the challenge, if we just directly pass it to the estimated solver, is that they have this universal quantifier on the program variable v, and this is really difficult. So the solution is to use these theorems for the quantifier elimination, and this is our main theoretical technique. So we use Farkas lemma for linear transition system, and then use Henneman and Putiner for the polynomial transition systems. And after this processing, we output a system of quadratic constraints with only the existing show quantifier on the template coefficient. So v doesn't appear here. There's no universal quantifier here. And this system can be efficiently solved by SME2 solvers, so we get the solution. And next, we introduce each of these three theorems. Firstly, using Farkas lemma, suppose this works for the linear systems. So suppose the constraint is like for all v, then if some polynomial on t and v are non-active, then it implies that g is non-active, and all of these f and g are just linear. Then by Farkas lemma is saying that this is equivalent to saying that g can be represented as a non-active linear combination of all the f's. So these, at the left-hand side and the right-hand side, if you think of them just as polynomials on v, and then two polynomials are equal, only if each pair of corresponding coefficients are equal. So, and the coefficients are just expressed by constant and then template coefficients. There's no v in this coefficient, so we get another constraint system that only has t and some new lambdas, and then some non-active constraint without v. Okay, this example. Suppose we have program variable v's and the template variable t1, t2 that we want to solve, and then we have f1, f2 are polynomials on v, and then g. And our goal is to find t1, t2 such that for all value of v's, if f1 and f2 are non-active, then g is non-active. Then by Farkas lemma, it says g can be represented as linear combination of f1, f2, and coefficient of each term should be the same, and term for the constant is g is like this, and then term for the term v1, for the term v2, for the term v3, the coefficients are like this, and these coefficients should be equal. And then we also have the lambdas should be non-negative. Then this thing is a constraint system with only existential quantifier on the template coefficient. So we can pass this to SDMT solvers, and they give us a solution, and one possible solution is this. And then the value for T1, T2 are what we need. And for polynomial case, we need other theorems. So Handelman basically says that so the constraint foreign is still similar, and he says that it's equivalent saying that G can be represented as a linear combination of F1, F2, but also contains this F1 squared, F1, F2. So basically, linear combination of all products of powers of Fi. So, and in practice with bounded degree, so it can be represented finitely. And then again, two polynomials over V are equal. We just match the coefficients and get new constraints without program variables, and then we can solve it. I have a simple example here. Like the Handelman's theorem can infer such kind of constraints. Like if V1 is non-active, then V1 squared is also non-active. And there's can be a more complicated example, like we can have system like the two linear inequalities can imply a quadratic inequality by representing this quadratic inequality as linear combination of F1, F2, and then F1 squared. And then match the coefficient, get a constraint and solve it. And then a stronger version is Poulinar's positive ansatz. The intuition is that the sum of squares is always non-active. So without any premise, then these expressions are always non-active. So we can use this and say that, okay, G can be represented as sum of squares plus this thing, where Fi's are here, non-active, and then Hi is sum of squares over V, which is automatically non-negative. And this also can be represented by finite template variables. So with this, we can imply something like this from nothing. So summary, we have these theorems, and with these theorems, we can transfer these constraints with this universal quantifier to the new constraint without this V, but at the cost of increasing the number of template coefficients, these lambdas. And then we have experiments showing that, first the toy one, showing that we can solve a nested loop case. This is code for a simple nested loop, and then this is the polynomial transition system. And Asparagus, our tool, can synthesize the exact quadratic gas bound. And we also perform an experiment on large data set. We compare with GasStep, which is the only work that estimates parametric gas bounds using some recurrence analysis. But it fails on nonlinear polynomial functions. And we also compare with Solidity compiler, which only estimates constant gas bounds. And the dataset we compare is the dataset used in GasStep. It has 24,000 contrast dismant functions. And we show that we are really better than all of the other methods. Firstly, we successfully synthesize gas bounds for much more functions. Like this is, we solve 86%, while they only solve around 60%. And our bounds are also consistently tighter. Like we are tighter compared to a GasStep in more than 97% of the cases. So we are really better in experiment. So there are some failure cases, and the reason is that might be too many variables, too many branches, too many loops, so our estimate to solvers still get stuck. And it's also possible if it's dependent on some untracked information, such as length of nested arrays due to some weird thing in Ethereum. So that's it. In conclusion, we propose Asparagus, a tool to automatically infer parametric gas upper bounds for smart contracts, and we use algebra geometry theories for efficient quantified elimination that is not done before. And it's sound assembly complete for polynomial transition systems. And in experiment, we vastly outperform previous tools. So thank you for attention, and I'm happy to answer any question.
Thank you. So we have a microphone here in the middle. If you want to ask a question, if you could please just go to the microphone. That way we can try to do it quickly.
Hey, that was very interesting. Thanks. So I had two questions. The first one's kind of quick. How much overlap was there in the failure cases between GasStep and the Solidity compiler? Like, did Asparagus fail on a subset of things that GasStep also failed on, or did it? Was there like no overlap? Yeah, sorry. So the cases, like the failed cases, the 13%, like, is that 13% like a strict subset of the, I don't know, like 38% that the Solidity compiler failed on, or is it different?
Yeah, it is almost with maybe 2 or 4 like different that we didn't solve, but they solved. But comparing to these tens of thousands of functions, then it's really negligible, and that's mostly due to the we use some tools to transform the Solidity code to the bytecode, and they might have some more optimization to parse more information than us. So it's not about our theoretical ability.
Cool,
Thank you
thanks.
for the question.
Yeah, sorry, just one more. Did you guys measure the performance of the constraint solving? Like how long it took to just solve the constraints?
So in reality, we just set a timeout. We set timeout for only 10 seconds. And so we compare with GasStep, it's also use 10 seconds timeout. So it's a fair comparison. If we have more time, we might solve more cases.
Okay,
Yes.
thanks.
Thank you.
Hi, thanks for the nice talk. So you said that you work on EVM bytecode, is that right? Like, are you analyzing the bytecode?
Yes, so here we work on bytecode, but more specifically, we need some tool to just tell me that what the variables, like in the bytecode is just push pop, and we need to analyze like these are the stack variables and corresponding to the program variables in the source code, and we use other people's tool to do this. So finally, we just got our polynomial transition system.
Right. So my question was actually, so sometimes people write these smart contracts with inline assembly, and I was just curious if you have any issues with handling inline assembly, or if you have encountered that.
I don't know. I think in my data set, every code is just source code, and then we use other people's tool to do that, and this is not our main contribution. Our main contribution is how we solve the constraints and how we use these theorems to reduce the constraints.
All right, thanks.
Thank you.
Thank you very much. Let's have one more round of applause for our speaker. Okay, our next talk is called Equality Saturation Theory Exploration a la carte. This paper earns the Session Special Award for Most French Paper Title. A la carte, okay. It will be presented by Anjali Paul. Am I pronouncing that right? Okay, great, thanks.
It's like doing a multiple desktop thing. Sorry. It's like not, the presenting is going to the other desktop if I do. Okay, sorry about that. I'm Anjali. I'm excited to talk to you today about rule inference for equality saturation applications. So first, jumping right in, I'm not going to do a big background on equality saturation, but the very basics that you need to know to understand the rest of this talk are just that equality saturation is a technique that uses this data structure called an E-graph, and it constructively applies a set of rewrite rules to compactly represent lots of equivalences simultaneously. But equality, and it runs this until saturation, or more realistically, until it hits some kind of resource limit, like a time limit. And equality saturation is everywhere. There's lots of recent papers that are doing interesting things with EQSAT for different applications. But equality saturation is only as powerful as the rules that you use. And writing rewrite rules by hand is really hard. It's time consuming. It takes a lot of engineering effort. It's difficult to validate the rules, which compounds the fact that a single unsound rule can compromise the soundness of your whole system. And it's difficult to debug the rules, both the rules themselves and also the performance of the rule set in your tool. So because of this, there's been some work recently in trying to learn these rules automatically. So here are just some recent papers on automated theory exploration and rule inference. But despite all of this recent work, building and maintaining rule sets still requires significant engineering time and effort. So we hypothesize that traditional theory exploration is too inflexible. We propose programmable theory exploration implemented with the Enumo DSL, which we'll talk about in a little bit. And we'll show that this scales better and enables new strategies for rule inference. So that's kind of outline of what I'll talk about today. But diving right in, so traditional theory exploration typically follows this three-step pipeline, where first you enumerate terms from the domain, then you find rule candidates, which naively would be the full cross product of your enumerated terms, but these traditional theory explorers have kind of clever techniques for finding rule candidates, usually by sampling from the domain. And then finally, you need to select a subset of your rules from the rule candidates that are sound and that are minimal in some sense. And so users of traditional theory explorers are usually expected to provide these three inputs: a grammar, an interpreter, and a rule validator. The grammar tells you how to enumerate terms from your domain. The interpreter tells you how to evaluate those terms on concrete values, which is used for the candidate generation that I mentioned. And then the rule validator tells you whether the rules that you find are sound. So given these three inputs, you run through the theory exploration pipeline, and you get out a rule set. So sounds great, right? But the problem is that it's not modifiable. It's a pretty one-shot push-button approach, and so it's not easy to make changes if it doesn't do exactly what you expect it to do. Also, the candidate generation and rule selection steps typically have hard-coded resource limits, which can be a problem in practice. And term enumeration doesn't scale, and usually these traditional theory explorers do exhaustive enumeration, and it's pretty difficult to encode other enumeration strategies into the tools. Also, you need an interpreter. If you can't implement an interpreter for your domain, you simply cannot use these traditional theory exploration techniques. So now I'll talk a little bit about how we solve some of these problems by using a DSL. So the first thing that I want to talk about is we can kind of all agree that the term on the left is less likely to lead to an interesting rewrite rule than the term on the right, and we just sort of have this intuition. So our insight is that users have intuition about what parts of the domain are worth exploring, but existing tools don't give you an easy way to leverage that. So what we're going to do here is we're going to turn the Theory Explorer inside out, and we're going to expose a small set of useful operators for rule inference. And the best way to look at that is just by examples. So the basic data type in Enumo is called a workload. You can think of it just as a list of terms. So here we just have literals from some domain. You can also use a workload to represent a grammar. So anywhere you see all capitals, you can think of that as a non-terminal from some grammar. And then you can compose workloads together. So here we're going to plug expers into itself. And let's take a look at what the plug operator does. So it takes two workloads and a string, and it's going to give you all of the combinations of replacing that string in a term from W1 with a term from W2. So an example here, the first term, x, there's two ways of replacing that with a term from W2, right? You get 1 and you get y. And then the second term, foo xx, again, we're going to replace the x anywhere we can with a term from W2. And so you can see we get this kind of like cross product of terms from W2 in the expression from W1. So using the plug operator, you can easily construct these kind of patterns of terms, right? So if we plug the literals into the products workload, we're going to get all of the ways of multiplying two of these atoms. And then if we plug that workload that we just constructed into sums, we'll get all of the ways of making a sum of products from this domain. So you can see how you can use the plug operator to kind of incrementally compose and construct these workloads that target parts of your domain. So going back to this example from the grammar, if we plug exprs into itself and then plug in the literals at the leaf nodes, what we're going to get is terms up to depth 2 from this grammar. So you can easily use plug to do exhaustive depth-first enumeration. But remember, our goal here is to actually infer rules, right? So what we've done so far basically covers the term enumeration step of traditional theory exploration. And then Enumo also has operators to find candidates and to select rules. And then we can also filter workloads. So here we're going to plug E2 into E1. That looks something like this. And then we'll filter by size 4. So we'll filter out all of these terms. But you can see that the last term in E2, 4 plus 5 plus 6, is already itself bigger than our size filter. So what we actually might want to do is filter on E2 first, and then plug that in and filter for size 4 there, so that we don't have to expand out the full plug and then filter it all the way down. So it turns out this optimization is super important because plug also grows exponentially, so it's important to keep the size under control where we can. And this is just stated a little more formally that you can, a filter of a plug is the same as filtering the plug if you also filter on W2 first. But for this to be valid, you need F to be a monotonic filter, which just means that for every term that satisfies the filter, every subterm also satisfies the filter. So here's a couple of examples. Excludes is monotonic, contains is not, right? Because you have this subterm that doesn't satisfy the filter even though the full term does. Okay, so that's a really fast overview of the Enumo DSL. Now let's see how it actually works in practice to find rules. The first thing we did is we compared to Ruler, which is an existing tool for theory exploration, and we find that pretty short Enumo programs are able to find rule sets that are strictly more powerful than rulers. So the second to last column, this column in green, is showing that Enumo's rules can derive all of the rules found by Ruler, while the last column is showing that the reverse is not true. Ruler's rules cannot derive all of the ones that we find with Enumo. Please look at the paper for more about derivability. I'm not really going to get into it in this talk, but the very high level is that more rules are not always better, and we give some definitions and metrics for how to measure proving power of a rule set. Next, we wanted to see how Enumo scaled to large grammars, because we know that can be a bottleneck for traditional theory explorers. So we were inspired by the halide domain, mostly just because it's a pretty big grammar. So we scraped out 725 rules from halide, and we tried to learn them with Enumo. The first thing we did is exhaustively enumerated up to a size bound. And since this grammar is pretty big, we time out after size 5. So we can learn rules that derive 42% of halide's rules up to size 5 in this grammar, and then with traditional techniques, you'd be kind of stuck at this point. But since Enumo has these like composable operators that make it easy for domain experts to leverage their intuition, we can kind of see that, like, okay, we know which operators here are closely related and so are more likely to lead to interesting rewrite rules. So what we did is we constructed an Enumo program to first enumerate just the Boolean operators and learn rules there. Then we enumerate just the rational operators and learn rules there. And again, for the predicates. We can compose these all together, but we also know that there's going to be some rules that use overlaps of these operators. So then we can write some custom workloads, again, using Enumo, and put it all together with an Enumo program that is just 140 lines, so it's not very long or hard to write. And as a result, we learn 845 rules that are capable of deriving 90% of halide's rules. And the point here is just that with guided search and with these composable workload and rule set operators, you're able to make progress past the point of exponential blowup, which is unlike traditional theory explorers where you're just kind of stuck as soon as things blow up too much. Enumo also enables entirely new strategies for rule inference. One of them is called fast forwarding, which is a phased approach for finding shortcut rules. It's pretty short. We implemented it in less than 10 lines of Enumo code. And the really exciting thing about this algorithm is that it doesn't require an interpreter. Here's what the algorithm looks like. I'm not really going to go through it in detail, but happy to talk about it more later. Instead, I'm just going to talk about an example. So Herbie is a tool that uses equality saturation to reduce error in floating point expressions using rewrite rules over numerics. This rule you might be able to learn with traditional techniques. This rule you can't, because equality is not decidable for the real, so you're not going to be able to write that interpreter. Now, you might be able to rewrite your sine and cosine in terms of complex numbers and then apply rewriting over those terms, but this is unlikely to scale due to resource limits. So what we do with the fast-forwarding algorithm is we start from an initial set of rules, and we strategically grow and shrink the E-graph, and then we extract rule candidates from the things that merge so that we can find shortcuts through the rule set to improve the results under resource limits. And here are some of the examples of rules that we actually find with fast forwarding. We have trig, we have exponentials, we also have CAD models. None of these are domains that are supported by existing tools. To measure the effectiveness of these rules, we plugged our rules into Herbie, the tool for rewriting floating point that I mentioned. All the way on the left here, we have the expert written rules. All the way on the right, we have the prior state, the art of inferred rules. And we show that Enumo is, while we're still a little behind the expert written, we've made a lot of progress compared to prior inferred rules. We also measured the effectiveness of Enumo's synthesized rules in the 3D CAD domain by using this tool called Selinsky that does equality saturation to shrink ASTs for 3D CAD models. And we find that the Enumo synthesized rules nearly match the performance of handwritten rules for that domain. Last thing I'll talk about is porting rules across domains. So for BV4, it's pretty fast and easy to synthesize rules, while for larger bit vectors, it's quite a bit slower. So what we did is we wrote an Enumo program that can synthesize rules for BV4, and then we cast and revalidate those for BV128. And basically, we find that the ported rules have almost as much proving power at a fraction of the cost compared to directly synthesizing for the domain. That's just about all I have. Ryan Chua, our amazing undergrad, also had a poster, so please talk to him as well, especially about that Selinsky case study. And I'm happy to take any questions.
Hi, great talk. So I have a question. So if I were to try to solve this problem, like what you showed at the beginning where you said, I think you agree that this rule is more natural than this other one. Mm-hmm. And the point of naturalness is that like, if you had a model of what languages look like, the ones that you're extracting rules for, you could target yourself towards most likely patterns rather than just patterns that never appear in practice. Like the not, you will never find that in a language. So you shouldn't experiment. And so there is a little bit of work on, I wonder basically if you can learn a model, think of it as like a probabilistic grammar of what programs look like. So if I had such a grammar, one that says not is very unlikely, then can your language capture this probabilistic approach? Basically say only explore, instead of depth first up to 4, explore the most likely terms according to some probability distribution. Like, is your language already ready to do that?
Yes, we don't already support probabilistic enumeration, though it's a really interesting idea and I think would probably not be too difficult to add. We also can support, like if you have a real workload of terms from some like actual like application, you can make an Enumo workload out of those.
To make it easier, instead of probabilities, I can take the negative log and then just say not just cost a lot, cost like 10. Then can you already do? Like
not in the enumeration. You can include that in the cost model for extracting rules and say like, I don't want to extract a rule that has like more than 3 negations or something like that. Yeah.
Thank you so much.
Yeah, thanks.
So yeah, thanks for the wonderful talk. So if I understand correctly, your DSL outlines a space for exploration, but if you find a rule in this space, how do you know if the rule holds or not?
Oh, so the user of the domain will provide a rule validator that will check the soundness of the rule. And so when we find and minimize, give you like a minimized set of rule sets, they're sound up to the soundness of the verifier that the user provides.
What validator do you use in your evaluation?
So most of the domains that we've implemented, we encode to SMT for the validator. Yep.
Okay, thank you.
Okay, thank you so much. Let's have another round of applause for Anjali.
Yeah, thank you for a nice introduction, and thank you for coming to this talk. I'm Gangi Park from UW Medicine, and today I will give a talk on synthesizing specifications. Consider you're writing a code, then every program should be accompanied by a specification that describes important aspects of the code's behavior. Specifications have many use cases like test, verification, repair, or synthesis in iterative refinement of code. However, writing good specifications is often harder than writing the code itself. So our question is, can we automate the extraction of specifications? And that analyzing consequences of a program has many applications. Not only a single function, one may want to extract relation between methods within a module. And it is also related to sensitivity analysis for some differential privacy, or can be used to abstraction of domain that is difficult to reason about. Thus leads to our problem, the specification synthesis problem. Input to a specification synthesis problem is a program that contains function semantics and a set of variables of interest, and a language for the search space to the properties. For these inputs, we aim to synthesize specifications, which is expressible in language L. They're sound, which means assertions hold after running program, and precise, which means no valid assertion in L is more precise than each of assertion. And we want the set of assertions to be complete. It means that adding any valid assertion in L does not strengthen the set of assertions. Let's see what they mean in figure. See, a property of language can say about equality between lists and comparison between size of lists. You don't need to parse the language, so let the language go away. The assertion that saying input and output list must be the same is expressible in L, but this is unsound, because that is not true for some valid input and output pair of the reverse function. A different property, saying the input of output list is greater than or equal to the size of input list, is sound. But it is, because it is true for every input and output pair of the reverse function, but still not precise. Because there exists a better property that says the length of input and output list must be the same, and which is precise. But sound and precise properties are not unique, and our goal is to find a set of properties that is complete. Actually, these two properties form a complete set of properties, which means that the intersection cannot be smaller than this. The key contribution of our work is to provide an algorithm to define specification in user-provided language that are provably sound, precise, and complete. In contrast, many approaches to find specification, like the icon of QXPEC, are based on dynamic techniques and sacrifices soundness guarantee. So, how each specification is synthesized? The algorithm uses three components: synthesize, check soundness, and our key component, check precision. The synthesis is example-based. Again, let's consider the properties is definable in the last L. What synthesize function does is to find the property in L that satisfies all the positive examples and reject all the negative examples. It would be nice if synthesize always return a sound property, but because it is example-based, it may give unsound property. That is why we need check soundness. Check soundness returns an example that must be true but not covered by the current property. And suppose we now have a sound property after synthesizing a property again. Then check soundness will say this is sound, but it may not be precise, so we move to check precision. Usually, checking precision of a property is harder than checking soundness. Say we want to find a property that is more precise than the current one, only using examples. But how can we convince that the new property is more precise? Well, it should satisfy all existing examples and need one more negative example that was not rejected by old property, but rejected by new property. And again, finding new properties also example-based, so we should check the soundness again. Now, the property is sound and precise, then the algorithm returns the property. Let's see a running example. First, we synthesize a candidate, and you found the sound property true, which is on for every program, and move to soundness check, and the check say the property is sound, and move to precision check. Precision check returns a new candidate saying that input list and output list must be the same, with a negative example that input list is empty and output list is 1,2. It moves back to soundness check, but it fails with new positive example with input list 1,2. Then it go back to synthesis. Now a new candidate is that the size of output list is greater than 0, which is unsound. So at soundness check, it fails again with positive example with empty list. And go back to synthesis again. Now I found some candidate that is sound. It passes the soundness check and move to precision check. Actually, this is one of the best property in L, but check precision may fail because our algorithm is example-based. Check precision finds a negative example with input list 1,2 and output list 1, and new candidate property says that the length of input and output list must be the same. It passes the soundness check and passes the precision check. So we are done. This is the best specification. But are we really done? Actually, we have a missing case. What if the synthesis fails? We will not go in detail how can we reach this situation, but say we have this set of examples. Each negative example can be rejected by some best specification, but there is no sound specification that rejects both negative examples. This can happen because positive example must hold for every property, but each negative example is specific to each property. One way to handle the conflicting negative example is to discard all the negative examples and resume the synthesis only with positive examples. This idea has been used in a tool Element, which targets to infer wikis library specifications. More recent approach is to use a stronger component, max synthesize, that finds a property that satisfies all the positive examples and rejects negative examples as many as possible. This approach has been introduced in a work that's synthesizing abstract transformers of a function. Here, we suggest a new approach to handle negative examples efficiently without max synthesize. Say we found the sound property. Our observation is that either the property itself must be a best, or there must be a better property, the best property in blue circle. It means that there exists at least one best property that rejects current set of negative examples, so we can consider them safe and remember. That is the idea of freezing negative examples. So when we have conflict, we can only remove unfrozen examples and resume the synthesis with the sound property we have found. Okay, then let me show some result. Our paper applies this algorithm for 4 different domains introduced at the beginning. In this talk, we will introduce only first 2 applications. We evaluated those applications using a tool implemented by us, Spyro. Spyro implements 3 components using a program synthesizer sketch by considering property language as a program language syntax and asking to find a term that satisfies examples. But the problem to sketch was to give soundness guarantee only up to bounded input size. So we used an external tool, Daphne, to check that properties are actually sound. All the synthesized properties were sound, but properties from 23 among 35 problems were proven sound without manual effort. And except 2 problems, we were able to prove soundness only with simple invariants, like output of length function is non-negative. Let's see some specification mining example. The first example is to find properties of recursive sum function that returns sum of integers between 0 and x when x is greater than 0 and return 0 otherwise. The property language allows disjunction on polynomial equalities or inequalities. It successfully finds 2 cases of output but it does not say about when each case should be chosen. One more complex formula that is hard to parse, but it says only the first distance work when x is less than 0, and the second distance must be chosen when x is greater than 0. A different example is list element function that checks if a list has an element of value v, and here property language allows a bounded quantifier L, where the semantics of quantifier is provided by us. Again, it is not easy to parse, but Spire was able to identify that the output is true if and only if there exists an element of v in list L. And not only a single function, Spire could also synthesize hyperproperties by giving programs that contain multiple function calls. It found that applying push and then pop should give the same tag and integer that was used as input to the push. And next one is algebraic specification synthesis. A paper from Marion et al. Introduced a technique to synthesize program from algebraic specifications of library module. One of their claims is synthesis from algebraic specification is faster than synthesis from full implementation. So what they did in their benchmark is, say we are implementing a hash map from array list, then synthesize one from mock implementation, and synthesize one from algebraic specifications, and compare the performance. From this benchmark, we try to extract algebraic specifications from implementation and compare them with the specifications manually provided by authors. In most examples, we could get the set of algebraic specifications containing what they have manually provided, but except for two cases. We will show here those two interesting cases. One is array list. A specification manually provided by authors is this one. Retrieving a value from an index after setting a value to that index must yield the same value. It seems correct, but a specification synthesized by Spire is this one. It says that, oh, you missed to check the index range. It shows handwritten algebraic specification is prone to error. Another example is specification of hash map. Again, the specification manually provided by authors is similar, but now it is correct because hash map doesn't need index range check. However, specification synthesized by Spire was just true. So what happened here? We manually investigated the code and found that the handling of hash collision was incorrect. So Spire also helped to find implementation error of program. Now, let me give the summary of our work. The first key point, our problem is to find a complete set of sound and precise L properties with provable guarantee. And our algorithm is example-based inductive synthesis that using three main components: synthesize, check soundness, and check precision. Here the check precision is the second key point. The third point is how to handle conflicting negative examples. We remember safe set of negative examples and revert to such set when conflict happens. A missing but also keyword is, in this talk, we showed how to synthesize all best property, but our paper explains how to synthesize all best properties. And our future work includes guaranteeing unbounded soundness without external verifier like Daphne, and synthesizing more complex logics like separation logic or temporal logic. Thank you for listening to the talk, and I'm happy to answer any questions.
Hi, so I have one question about, two quick questions. So one is like, you didn't say how do you synthesize a candidate. So are you enumerating all the possible functions?
Oh, that's a good question, but we can use any technique of, any program synthesis technique from example. But our implementation uses Sketch, and Sketch is kind of reducing a program synthesis problem to a single SMT query. And
so in Sketch, you have to give a template. So are you giving a template there? Like?
Oh, yes. We also provide some template, but
okay.
But for the property, we only provide the grammar, and so
Okay, then it
yeah, just the
enumerates
grammar
all
is
the
template
possible- okay,
from us.
correct. And okay, second question is about precision. So might be a stupid question, but why don't you just generate a lot of candidates and just take a conjunction of them? Because if they're all sound, then the conjunction is also sound. Like, isn't that precise? Like, what's the definition of preciseness exactly here? Like,
Yeah, that is also a great question, but the size of grammar we use in this experiment is sometimes is more than billion, and usually it's more than 10 or 100 million. So it is too big grammar to enumerate all the sound properties, and even and for precision, we should compare all the sound properties. So it's square of the size of the
so in
grammar.
the definition of precise, you're also taking the size of the specification as some factor to decide whether this one is more precise than the other one.
Here, the size means it's the size of the search space. So.
Okay, maybe I'll talk to you offline then. Thanks.
Hi, thank you very much for the talk. And I have a question about the freezing negative examples. Yes, you have mentioned that it will be quite difficult to certifying all negative examples, so you need to turn synthesis to maximum synthesis. And I'm quite wondering that if your grammar includes some and or operators, so you can just synthesize for each negative examples and just take the junction or something, get a specification more precise. So what is the difference between it and the maximum synthesis?
Actually, if we remember, so our paper explains that if we remember the set of negative examples, then the removing all the unfrozen example is equivalent to max synthesize, because it only removes this at most one negative example. So we're implementing max synthesize without only using synthesize. So
I see. Yeah. Thank you.
Okay, I'm going to make it really quick. So I didn't understand the completeness. So the idea of completeness is that there are no other sound properties in L beyond the ones you've already discovered, correct?
Yes, that's correct.
But if the grammar is infinite, this is not an easy problem to solve. So I don't. How do you check completeness? What's the maybe if only for specific logics or some encoding, something like that. So yeah, that's the how do you check completeness, and why do you think it can always be done?
So. So how we synthesize all the specification is that we modify a check precision a little bit so that we find a negative example that the negative example can only be drawn from the conjunction of existing properties. So if such negative example cannot be found, then it means that the conjunction cannot be smaller than the current one. So that's how we check if the conjunction is complete. Okay, and actually we need some assumption on the language that sometimes the easiest condition is that the language is finite, but it is true that you need some assumption on the language to say determination.
Then it's clear. There is eventually a solution, so that's okay.
Yeah, yes.
Okay, thanks. Solvable or something like that. Okay, that works.
Okay, thank you very much. Let's have one more round of applause for our speaker.
Okay, give me a second. Oh, here we go. Oops. Okay, thank you for the introduction, and I'm Yifei Huang. Today I'll be talking about explainable program synthesis. So the program synthesis problem where asking the users to provide their intent in the form of high-level specifications. The specification can take various forms. It can either be some input-output examples, or some logical formulas, or some demonstration. And submitting the specification to the synthesizer is responsible to generate some function f that is guaranteed to be correct. And over the last 15 years, there's been a lot of work in this field. People have proposed many sophisticated algorithms like probabilistic enumeration, conflict-driven learning, building libraries, and etc.
And people has also built a lot of exciting applications using this algorithm, like synthesizing compilers, network processes, robot controls, and all different kind of end-user programming. So all these program synthesis techniques or applications, we have one big hope. That is, we want to allow the programmers to more freely express their intent. But despite having a lot of this good synthesizer, it seems that no one is really using it. No one really wants to use the synthesized code in their real working environment. So what is happening over here? So let's take a look at this example from a very recent program synthesizer by Alice. So in this example, we are trying to synthesize a lambda formula that is sorting a list of integers. So as you can see, the specification are given as an input-output example in the upper right corner, and this is a final result. Notice that to accomplish the final result, the synthesizer also comes up with a lot of intermediate routine. So the blown-up version of the implementation is actually very complicated and very hard to understand. And even in the paper itself, the author has to provide useful names for each of these individual routines to really convince the reader that the function itself is indeed correct. So this raises the central question of this paper. How do we help the programmers understand the synthesis implementation better? Well, let's just take a deeper look at the previous example. Say the user wants to understand the function C13 over here. So one approach to do that is like, what about we just put the input and print the input output of this function? They just insert two statements over here, and we pass one of the I/O example from the global function f. And then we got this for tuple over here. And by staring at it, we might say, oh, okay, so it's very likely that C13 is calculating the maximum element of this L. L indeed is. So question solved. No, exactly. This might work for this case, but let's take a look at the next example. So here is also a specific synthesis problem that we're taking a list of I/O examples that they're string in this case. And we submit this specification to a very famous scikit solver, EO solver, and we obtain this implementation. We know that from the theory of the synthesizer, that the synthesized program is guaranteed to be correct. But if we submit this program as well as the specification to another SMT solver, CVC5, it actually rejects it. So how do we diagnose this problem? So remember in the previous example, we're using print statement. The print statement is exactly answering the question like, what is each individual expression is doing in this program? But it's really not that straightforward to conclude why this program is wrong or really localize a faulty location of this program. So a more smart question would be, what should this sub-expression do in this case? Well, assume that we have an oracle in this case and give us an answer to this question. So actually, surprisingly, the oracle says nothing can be done in this case. What does it mean? It means that no matter what kind of expression you replace in this blue box, the function is wrong. So there's no fix in this case. So actually, the real place you need to look at is the later part. And so then further investigation revealed that it's actually this yellow box of substar has a discrepancy in the semantics in both CVC5 and EO solver. So we'll see by asking a smarter question, we'll be able to solve the problem or to understand the problem deeper. So with this question, it motivates our main contribution to this paper. That is the concept of sub-specification, which I will refer to subspec for shorter. So to define or understand the definition of subspec, we will need some implementation F that is already satisfying the specification phi, and some specific location H at the function F. And there's at a location H, there's a subtree G over there in the AST. And one thing we can do over here is that we can replace whatever sub-expression at G with all different kind of legal expression over here. And by doing that, we get a family of function F. Well, some of them satisfy the original specification, some of them are not. So the definition or the concept of sub-specification is really trying to capture all the possible alternation you can put at a certain location of a function F. So let's just take a look at a very concrete example of the subspec. Let's just revisit the previous example. In this case, we observe that the input-output of C13 in this case is this for triple. And surprisingly, the conjunction of these four examples are actually the subspec of C13 in this case. But is it always the case? Not necessarily. Let's take a look at a logical formula. And this is a logical formula given, and we have some synthesizer to give this result. And if we want to understand what kind of alternation can be put as if conditions over here, with the help of subspec, it actually tells us every asymmetric function can be put over here. So possible alternative implementation is actually just the negation of the original functions. So from this example, we can see that it's not just about input-output examples. Input-output example is not always the subspec. And the subspec itself is actually well-defined in all the fields. It's no matter in logical formulas or I/O examples. And it actually provides more information than print, because in print, you will never be able to tell what kind of alternation you can do over here. So let's take a look at the one last example over here. This is one of the specifications drawn from the SPLASH' benchmark 2018. As you can see, it's a quite complicated example, and the implementation itself is rather simple. And if we calculate the subspec for the two locations over here, you can see it's actually surprisingly simple. And actually it tells you there is nothing really too much you can do in this program. So one of the few possible alternate implementations is just to replace the else branch with 2. So in this case, we'll see that even despite the original specification is very complicated, the resulting subspec itself can be very simple. And with this simple subspec, it also tells you how you can do the alternation of the original implementation. Okay, so now we have motivated concept. And for the rest of the talk, I'm going to focus on how this concept can help users and how we can really obtain the subspec of each program. So we conduct a user study, which we have recruited 20 PhD students as our participant. They are coming from different fields, and we group them into different groups, and we conduct the repeated measure setup. So all the participants in different groups are asked to answer some questions. Across the group, some of them has the access to the subspec, and some of them does not. So the question of the task is something like this. The user are given a specification fee and some synthesized program. The synthesized program is not guaranteed to be correct, but they will be noticed if they're not correct. So we ask a question like, for example, can you name a function g that is a part of a function f? And can you replace g with some other g prime? And what does g do in f? And or some question like, how does f satisfy the specification fee? And also, in the case that f itself is buggy, can you really fix f? And we have a UI in this user study that the user can hover the mouse over the implementation. And when the mouse is hovered over each part, the corresponding subspec will be displayed over there. And so here's the user study. Here, as you can see, there's 3 types of questions we have over here. One is providing alternative implementation. One is to comprehend each part of the implementation itself. And the last part is about debugging. As you can see, this is the result for the scores of the participants that doesn't have the help of the subspec. It's actually pretty low, especially for a question like, why does f satisfy phi, the one that really requires your understanding. And with the help of a subspec, it's actually, we can see a significant improve in the accuracy of their response. To summarize, the subspec itself actually improves the response accuracy by 91%. So lastly, we're now shown that this concept itself is useful, but how do we get it? Well, actually, we developed a 2-stage algorithm. So in this paper, we have proved that actually, for most of the cases, it is very straightforward to construct the subspec. But the drawback of this straightforwardness is actually the subspec itself can be very complicated. So we have subsequently submit the first stage to the iterative simplification process. So in this process, we're using synthesizer itself to synthesize a simpler specification that is equivalent to the original one. In other words, we're trying to explain the program synthesizer using the synthesizer itself. So here's the effectiveness of the algorithm. So you can see the y-axis over here is a compression ratio of the second phases. So actually, the optimize is the final output. And the last one is the seed, that is the subspec we get in the first step, that is the straightforward construction. So as you can see, for the cycles task, 2/3 of the examples can achieve a compression rate of about 80%. And even for stream coder, which we don't have a very good, which the simplification algorithm cannot fire completely, we still can achieve a for 90% of dream coder examples, we can still achieve a compression rate of over 50%. And in terms of the efficiency of the algorithm, when compare the time to synthesize each subspec versus the time to complete the original synthesis task. So as you can see, for 80% of the request, this actually can be done in a time that is even shorter than the original synthesis task. And there's only few tasks that is really hard that takes more than 100 times of the original synthesis task. This shows that this algorithm itself is both very effective and very efficient. So to summarize my talk, we claim that the program synthesizers are becoming increasingly sophisticated, and to understand the implementation is taking more and more effort. So to handle this problem, we introduced the concept of subspecification to help explain the synthesizer's output. We also conduct a user study to demonstrate the usefulness of the subspec, and we developed a design algorithm to synthesize them, and we have also developed a lot of associated theory in the paper. Lastly, we implement our algorithm in the tool called S3. The artifact is available in this link or in this QR code if you're interested. And thank you very much. This is the end of my talk.
Oh, hello? Oh, really cool work. Is this limited to Cycus?
Sorry, are you asking that is it limited to Cycus?
Yeah.
No, actually, this concept can work for any program synthesis problem. And even in this paper, we have two domains. One is Cycus, another one is Dreamcoder, which is completely different. In Dreamcoder, it's actually synthesizing lambda formulas using I/O examples.
And in that case, what are the sub-specifications? What do they look like?
So for the Dreamcoder, actually, for most of the cases, is still a pair of input-output, but sometimes it is not necessary. For example, it can be operator. For example, the first of this list must be 3, but it doesn't put any constraint for the remaining of the list. Something like this. It's not necessarily just the input-output constraint.
Yeah. My last question is, when you compress the specifications to be simpler, how do you tell the synthesizers that you want a simpler one? Do you just give a smaller grammar?
Yeah, no, we're asking the synthesizer to synthesize a smaller program that is smaller specification that is equivalent to the original one.
So in the talk, you have shown like a specification from a competition, and that one looks pretty much more complicated than the implementation itself. So I'm just wondering, what is the point? Because for such specification is human unreadable, and I guess maybe that's the point. Also, you want to learn like some of the maybe more specific sub-specifications so that people can understand maybe part of the program well. So do you have any comments on that?
Yeah, I think you're asking a very good question over here. That indeed is a problem. That indeed is a very artificial examples, and we use them as a demonstration to see that this concept itself can be applied to different fields. But I agree that in reality you won't be likely to encounter a specification like that. But you can see even with that, our simplification algorithm actually works very well, and we can somehow find the essence of the specification itself.
Yeah, I mean, especially when the synthesizer program is getting complicated, and they will handle maybe different cases of specification, so that you can understand, like, split it into different parts.
Yes, that's true. I mean, because for the demonstration, we think that their simpler program might be easier to understand. I mean, we have some example that is rather complicated, but it might take too much space or too much time to explain.
Okay, thanks for your answer.
Thank you very much.
Okay, I have another couple of questions for you. I was really excited to see a user study here. So it's really neat. So I saw you had a bar chart showing comparing the result of your comparing results with sub-specifications to results without sub-specifications. And you said there was a significant difference, but I didn't see a hypothesis test. Did you do a hypothesis test?
I don't think we did.
Okay. So then we can't actually conclude that there's a significant difference, right, unless we do the statistics.
Yes, that's true. Okay, sorry, could you just repeat your question again? I didn't really catch it.
Yeah, so you argue that there's a significant difference between the two conditions, but I didn't see a hypothesis test that would actually show that statistically.
Oh, okay. I agree that might be a better approach, and maybe we should be more careful about that in our future work about the research user study.
Yeah, because that's important, because you could make the same argument with n=1. Look, we compared the medians, and the medians were very different. Right, but you actually have to look at the variance in the numbers and figure out, right? Okay, the other question I have for you is about the analysis of the qualitative data. So some of the questions that you asked the participants were sort of qualitative. If you go back to the slide with the questions, can you do this, and how would you, you had a few examples of questions a few slides back. Oh. I'm wondering how you analyze that data. So you're scoring the results to see, yeah, so why? Like the comprehension, the why question? How did you score the results of the why question?
So we have some certain, it's like you're grading the students' answers to a question, right? We have a certain point that is, there's certain key part of the function that is, for example, this function is calculating the maximum of the list. And then for example, a sorting function is you're getting the ith element at a time. For example, you get the smallest one, the second smallest one, the third smallest one. You need to capture the one or two of this crucial point. And for each of these problems, we design the crucial point. And if they hit the point, we give them a score. We are actually very mercy in grading. But still, I mean, without the substrate, also they're just answering something that's completely irrelevant.
Sure. Okay, neat. Thank you very much. Okay, let's have one more round of applause for our speaker. Okay, our next speaker is Zhenyang Zhu. Am I pronouncing that right?
Yeah.
Who will be presenting Pushing the Limit of One Minimality of Language Agnostic Program Reduction.
How to set which slideshow play from start? No, this is going opposite, right? Yeah. Yeah, so you have to choose the monitor. It's next to or reversed.
So I think there's a button in presenter view.
Oh, presenter view is putting the presentation there. And it should be opposite.
Wait, where's my mouse?
It's there right now.
There we go.
Okay.
So I think there's a button in presenter view.
Usually you can choose the monitor, right? Like which monitor you want to work on. No. You change the monitor.
Yeah. Sorry.
There a setting to like.
Fix this by pressing X. I don't know if X works here.
Okay, it's one. On the slideshow,
Yes.
go to slideshow, there's monitors. Is there a monitor choose?
No. That's weird.
Yeah, maybe that's. Do you want the presenter here? Yeah, I prefer to have the presenter.
Yeah, can we get AV chairs?
Can we like custom? Is there a monitor?
Here, let me check.
Okay, Alt F5. Like.
Setup slideshow. Yeah, this one. Click this one. Yeah, this one. Yeah. See, primary monitor, monitor 2. Yeah. Okay.
Yes, there we go.
Okay, thank you. Perfect.
Cool.
Thanks. Sorry about that. Hello, everyone. My name is Zhenyang Xu. I'm from University of Waterloo. Today I'll be presenting our work, Pushing the Limit of One Minimality of Language Agnostic Program Reduction. Debugging language processes such as compilers is usually a difficult task. A popular compiler often receives many bug reports from its users and developers. And to reduce the workload required for fixing these bugs, maintainers of many language processors explicitly encourage bug reporters to submit a minimized bug report, to submit a minimized bug triggering test case. For example, here I quoted some sentences from some of the most popular compiler communities, including LLVM, GCC, and Rust. And we can see all of them encourage to provide a minimal test case. And program reduction is a technique that can automatically minimize bug triggering programs. And this figure shows the task of program reduction. So as we can see, a program reducer will take two inputs. One is the program that has the property psi, and the other is a checker that can check whether a program has a specific property. And then the reducer will finally output a minimized program, which still has the property. And to apply program reduction to test case minimization, we can simply use the original large and complex bug triggering program as the input program, and then set the property to be that the program triggers this specific bug. And then the reducer can produce a minimized program that can reproduce this bug. And program reduction is a trial and error process. During the reduction process, a current best program will be maintained, and it is initialized by the input program. And in each iteration, the reducer will perform a transformation to the current best. For example, it may delete some code from it, and the variant will be obtained. And then this variant will be checked to see whether it still has the property. And if not, the reducer will generate another variant by applying another transformation. And if it passes the property check, then the current best will be updated with this variant. And the entire process will terminate if no variants that have the property can be generated by any available transformations. So Persis was the state-of-the-art language-agnostic program reducer. It is deletion-based, which means it only tries to remove tokens from the program. And meanwhile, it is tree-based, which means it performs reduction on the tree representation of the program. Specifically, you will first pass the program to get the path tree, and then try to delete nodes in the path tree in a top-down manner. And most importantly, Persis can ensure one minimality, which means that in the result produced by Persis, any single node cannot be deleted. So for program reduction, finding the global minimum is NP complete. Therefore, one minimality was proposed as a relaxed goal for program reduction, and the one minimal result can be actually considered as a local minimum. However, there can still be many reduction opportunities in a one minimal result. Here is a real-world example. This program on this slide actually can trigger a bug in LLVM, and these two statements that have the shift operations are the key to trigger this bug. And this program is the reduced version output by Persis, so it is one minimal. However, we will see that there are still many reduction opportunities in such a reduced program. So first, let's look at this highlighted code. We can see that this program, these statements passes the value of ID 0 to ID 6, and then to ID 7 to ID 8, and eventually to ID 1. So we tried to replace the ID 8 highlighted in yellow with ID 0. So the program directly assigned the value of ID 1 to ID 8 to ID 1. And we found the program after this replacement will still trigger the same bug as expected. But notice that after this replacement, the three statements highlighted in red becomes redundant. So we deleted these three statements, and still the program can trigger the same bug. So now we've already got a smaller result, but we can make it even smaller. So let's look at this type-def statement. This type-def statement defines an alias for the type short, and this alias is used once, which is highlighted in yellow. So if we replace the alias with short, then the type-def becomes redundant and can also be removed. And finally, we also found that if we remove the highlighted for statement and the keyword else at the same time, the program will still trigger the same bug. So from this example, we can see that there can still be many reduction opportunities in such a one minimal result produced by the state-of-the-art. And to further reduce a one minimal result, we can perform some non-deletion-based transformations to the one minimal result and possibly make it not one minimal. For example, we can change some identifiers or specifiers as shown in our example. And also, we can perform a more exhaustive reduction algorithm. For example, remember that in our last step, we removed the for statement and the keyword else together. And such a reduction opportunity can be seized if we try to remove every 2 nodes rather than just 1 node in the path tree. So based on these observations, we propose a framework called Vulkan. And this figure illustrates the typical workflow of the tree-based program reduction. And on top of this, Vulkan introduces a set of auxiliary reducers to help further reduce one minimal results. Each auxiliary reducer performs either a certain type of transformations or a more exhaustive reduction algorithm. And once a one minimal result is obtained by the main reducer in our framework, one of the auxiliary reducer will be invoked to produce either a smaller or a transformed result that still has the specified property. And this smaller or transformed result will be sent back to the main reducer for further reduction. And we propose a 3 example auxiliary reducer based on our observations, and more reducers can be actually added to this framework. So recall that in the previous example, we successfully removed more code by replacing an identifier with another identifier in the program. Therefore, we propose an auxiliary reducer to perform identifier replacement. So this reducer will first extract all the distinct identifiers in the program. And then it will choose an identifier, for example, ID 0, and try to replace all the ID 0 except the first one with another identifier in the program. Here the reason to keep the first one is that the first identifier usually appears in a definition or initialization. If all the following usages of this identifier are successfully replaced, then this definition or initialization will become redundant and thus can be probably removed. If this replacement makes the program no longer trigger the bug, this auxiliary reducer will try to replace it with another identifier. And if all the other identifiers have been tried, it will try to replace the next identifier, for example, ID 1. And eventually, it will find that if we replace the ID 8, highlighted in yellow, with ID 0, the resulted program can pass the property check. And this new program will be sent back to the main reducer, and the main reducer can further remove these redundant statements. And also recall that after this, we further reduce the program by replacing the alias with short. So we implement another auxiliary reducer called subtree replacement to perform this type of transformations. So this auxiliary reducer tries to replace a subtree in the path tree with a new one. For example, it may try to replace the subtree that corresponds to the highlighted alias. The subtree is shown on the left. The new subtree will be generated based on the formal grammar. For example, here we have the production rule of type specifier in the C grammar. And this rule basically shows what a type specifier can be. And with the guidance of the grammar, a new valid subtree can be generated and used to replace the original one. And finally, in the previous example, we also found that we can remove the for statement and the keyword else at the same time. To make such reduction possible, we proposed the third auxiliary reducer called tree-based local exhaustive enumeration. So here on the right side, we show the tree structure of this if-else statement. This reducer uses a sliding window with fixed length. We set the default length to 4, and the sliding window will move from left to right and top to bottom in the path tree. And for each position of this sliding window, the reducer will enumerate and test all the possible variants obtained by deleting elements in the window. For example, when the sliding window is on the leftmost, as shown by this blue box, the reducer will generate 11 variants by deleting elements from the window. And after test all the variants, the sliding window will move by 1 node. And when the window moves to this position, it will find that the for statement, which is statement 2, and the keyword else can be deleted together. This auxiliary reducer is inspired by a reduction algorithm in C-reduce. C-reduce is a reducer that's specifically designed for C and C++, but it also contains some language-agnostic reduction algorithms. The algorithm in C-reduce is list-based, and here we improved it by making it tree-based. And eventually, with Vulkan, the example we just saw can be reduced from 116 tokens to 56 tokens. To evaluate our approach, we implemented a prototype of Vulkan on top of Persis, and we used Persis as the main reducer in Vulkan. And we conducted extensive experiments with a multilingual benchmark suite, which contains 20 C programs, 13 Rust programs, and 93 SMT programs. And we choose Persis as our main baseline since it was the state-of-the-art language-agnostic reducer. And we also use C-reduce as our baseline in some experiments. First, we use these 3 tools to reduce the 20 C programs, and the statistical results are shown in this table. From the table, we can see that Vulkan produced smaller results than Persis in general. On average, the results of Vulkan are 35% smaller than those of Persis. And in this experiment, C-reduce is still the best, but this is expected because C-reduce is specifically designed for reducing C programs. However, interestingly, we found that if we use Vulkan to reduce the program output by C-reduce, we can even get smaller results. We also ran experiments with Rust and SMT benchmarks. In these 2 experiments, the results of Vulkan is 27% and 52% smaller than those of Persis. In terms of efficiency, Vulkan inevitably requires longer execution time. It is around 2.5 times slower than Persis in C benchmarks, and for Rust and SMT benchmarks, which generally take less time to reduce, Vulkan is 7 and 8.5 times slower than Persis. So to sum up, Vulkan can reduce more tokens than Persis. It actually trades off the efficiency for smaller reduction results. And also, like Persis, Vulkan is language agnostic. It is effective with different programming languages. And that's pretty much about my presentation. Thank you for listening. I'm happy to answer any questions.
So I have 2 quick questions. So first is that you talked about this identifier replacement.
Yeah.
So once you do the replacement, how do you test? What is the property pass thing? Like, what are you testing? That they're equivalent programs, or?
Sorry,
So my question is that when you do this identifier replacement,
yes,
you get a new program.
You're right.
And you said that this passes the property.
Mm-hmm.
So what's that property?
Okay.
I missed
so the property is always that the program can trigger that specific bug.
So it's not the program are equivalent. They can trigger.
No,
the same bug.
it does not need to be equivalent. It just have to trigger that specific bug.
I see. Okay, the second question is about, so you're in the example, like you had this successive assignment, and that you said that you can remove.
Yes.
So why don't you start from there and just find the successive assignment and then remove them? It might be a stupid question, but that's something which came to my mind first, that if you have ID1 equal to ID2, ID2 equal to ID3, something like that, then why don't you just do it initially in a pre-processing?
So we want this process to be like automatically done. So I'm not sure like how.
Because wherever you're removing these lines, it seems like a successive assignment, like just a like a.
Okay, if you like directly remove these statements without the replacement, then the program will no longer trigger that bug because it might be like rejected by the compiler in the early stage. Because, for example, the ID8 is not defined or something like that, and the bug may be at the, for example, following stage of that compiler. So if you directly remove the statements.
All right, thank you.
Yeah.
Thank you.
I noticed that both of the examples you had for the C program had sort of like the flavor of like just general compiler optimizations. I was wondering if you'd like looked at for like some adding other rules that like have an optimization flavor to them, whether that's like constant folding or something, and if those perform better than other rules.
Sorry, I didn't get your question.
Like in removing the assignments, like I would expect an optimizing compiler to do that, like once it's a lot further down the pipeline. But like that seems like a fruitful way to minimize programs in general. Are rules that look like that better than other rules, I guess? They like have this optimization-y flavor.
So
or did you look at that at all?
Sorry, I still didn't quite get the question. Maybe
we can talk about it offline.
Okay, yeah. Sorry about that. Thank you.
I'll make it quick. Hi. Do any of your transformations do function inlining? I know that we've found that to be useful in reducers that we've built
function, you mean use function inline to minimize the program?
Yeah, like you have a function that's called in one place, so you inline the function body and then do further reduction.
Okay, the point here is that we try to make the tool language agnostic, but like function inlining is kind of hard if we like if we don't have any knowledge of that specific language. Yeah.
Okay.
Okay, thank you very much. And let's have one last round of applause for all of our speakers.
Hello, hello. you don't have to do that. Yes, okay, so the
All right, hi everyone. We're going to get started. My name is Chandra, and I'll be your session chair. And first talk in this program synthesis session is Mobius, synthesizing relational queries with recursive and invented predicates, and we have Gund presenting.
Thank you, Chandra. So, this talk will be about relational query languages. So when I say relational query languages, I want you to think of languages like SQL, relational algebra, wherein OOPS Lab, where the programming language conference, some formulas that we might be more comfortable with is probably Horn clauses, and there are languages that are based on Horn clauses too. Prolog, Datalog, Answer programming, and so on. Right? This talk really at some level is answers the question how do you synthesize recursive Datalog queries. I'll explain what Datalog is and why recursion is hard in the next couple of slides. Right? So a Datalog program, what you see over there is the canonical Datalog 111 program. It's a program that finds strongly connected components in the graph. Right? Are two nodes x and y in the same SCC? Yes, they are. Well, two nodes x and y are in the same SCC. If there is a path from x to y and there is a path from y to x. When you say that there is a path from x to y, well, there are two cases. There is the base case of the inductor process, which is that there is a direct edge between x and y and there is the same path. There is a path between them, or if there is a transitive step, there is a path between them as well. Very straightforward to write. When you think about database queries, you think about queries in relational algebra, in SQL, these just have a flavor that's more similar to inference rules, if you will. And the meaning of a Datalog program is really, let's say that I give you a graph on a specific graph, the one that you see on the bottom left. The meaning of a database query, of a data query is to start with the input tuples. So which pair of nodes is there an edge between? Start those. Keep repeatedly apply these rules that I have written down on the left. Every time you apply the rules, you derive something new. And repeat this process until you hit saturation of some kind, until you hit a fixed point. And so the meaning of a Datalog program is really just the fixed point of the rules on the specific table that you're working with. Now, Datalog, my own introduction to Datalog was through my postdoc advisor, who has used it extensively for static analysis. There are dramatic examples of places where it's much easier to write a Datalog program. An analysis would take several pages, gets reduced to a couple of dozen lines of code. Right? And beyond that, there are also settings where it's used for knowledge discovery, for discovering, for declarative networking, and so on. And it's not just one of these academic pursuits. There are actually industrial engines devoted to solving Datalog programs. Now, when you think about all these languages, the first question that will come to your mind, regardless of the fact that we're in the synthesis talk, is the problem of evaluation. I give you a program, I give you a set of input tuples, what's the output tuple? Lots of papers have been published on this, and it's the focus of a lot of research. Papers are still being published on it, by the way. But what we are interested in this talk really is about the question of synthesis. I give you input-output examples, and can you learn a program that's consistent with the data that I have just provided? Why is this interesting? Well, it's interesting for us in the program synthesis community, well, because we are interested in learning more complicated, more expressive programs. It's interesting for people in AI and machine learning because they want to learn, they want to build agents that can reason. And beyond this, you might want to automatically learn a static analysis, automatically learn network policies, and so on, and this just feels like a foundational problem for all those settings. Now, given that it's a foundational problem, there has been a lot of work on synthesizing relational queries, synthesizing them from data. Despite all of this, there are a few challenges that remain. And I have listed three that stuck out to me at the top of my head over here. The first is about learning recursive and invented about learning programs with recursive and invented predicates. I'll talk about that in a second. And the other two are the usual suspects. How do you learn when your data is large? How do you learn when there's noise? As such, none of that will be the focus of this talk. We are focusing on the problem of recursive and invented predicates. And if you really want to think about this problem in a if I were to reduce it to its vulgar essence, right? The problem is really, can we learn how to find SECs if one doesn't know how to compute reachability? Lots of papers have attempted to solve this problem. What makes this hard is really questions of how do you know that there's an intermediate concept called a path that you should be looking for? How many such invented predicates do you introduce? What are their schemas? Over here, the path is a relation between two vertices. There's a path from a vertex to another. How do you know that the invented predicate has the same schema as any of the output relation that you are synthesizing? I'll give you an example of where it gets tricky in a second. How big can the rules get? The example that we saw of SEC, the rules were relatively small, but how do you know how big the rule should be? How many of these rules do you introduce? All of these basically, when those of us in the synthesis community look at a problem, we usually are the first technique that we reach for is some kind of enumeration, right? Or some kind of guided enumeration and so on. All of these things really just mean that enumeration is very hard over here. Most existing systems make some kind of assumptions that the user will tell you how many invented predicates there are, they'll give you a limit on the length of the rule and so on. All of these are really just begging the question, how is the user supposed to know? Right? Here's an example of a query that involves a particularly insidious kind of this kind of scheme, not just predicate invention, but actually schema invention. So let's say that I give you a graph whose edges are colored, and the relation that you want to learn is not reachability, but monochromatic reachability. Is there a path from A to B, all of whose vertices have the same color? And so what you see over here is an example data log program that computes monochromatic reachability. This rule RE over there has this relation path X, Y, C. There's a path from X to Y, all of whose edges have the color C. That's an invented predicate, but that doesn't share its schema with anything else. What we are finally interested in is there a monochromatic path from X to Y? We want to project out, yes, we need to keep track of C, but we are going to project it out eventually, right? And how are we to know that the invented predicate has this additional attribute in it? All right. But that's not all that there is in the title of this talk. The title of this talk says recursive and invented predicates. So let's talk about the non-recursive setting, right? And non-recursive settings, in the non-recursive setting, I claim that invented predicates are not really an issue. And there have been plenty of papers that solve program synthesis. For example, for SQL, several papers, a couple of papers that I've listed over there. And let me try to motivate why it's not an issue at all. So here's a program that computes the grandparent, that finds out if two people are cousins of each other. When are two people cousins? Well, when they share the same grandparent. Just inline it out. You don't need to talk about the grandparent to say that two people are cousins, right? And so the problem is that this notion of this trick of inlining everything doesn't work with recursive queries. How much should you inline? And our observation, really, in this paper is that for a given finite set of input-output examples, a finite unrolling is sufficient. So yes, you'll need infinitely many arbitrarily long rules to actually compute SEC. But for graphs that are sufficiently small, this set of 5 rules is sufficient. And so the question that we ask in this paper is really, if somebody shows you a program like this, can you stare at it long enough and recover the original recursive program? And so the architecture of our system is really to begin with an off-the-shelf non-recursive synthesizer, pass it on to this extrapolation algorithm, and from that we get a possibly recursive program P. And so the main goal of the recursive synthesis process over here is to generalize. And so let's imagine that we are trying to find strongly connected components once again, and the base, the seed non-recursive synthesizer looks at this pattern and finds out, makes a hypothesis about what SECs are. Now we claim that this rule over here is actually somehow an unrolling of some simpler set of rules. The question is, how do we find those patterns? And so the details over here, let me walk over them somewhat quickly. But the idea is that that rule over there doesn't expose any internal structure. It's just a monolithic rule. And so we first decompose it into its Chomsky normal form. And that suddenly forces invented predicates into the system. And it allows us to see the internal structure of the predicate. Now, if this is the same normalized non-recursive query, if these are the unrolling of some recursive program, then some of these predicates must be really doing the same thing. They must be playing the same role, right? So let's just merge the predicates, start merging predicates into equivalence classes. Let's do it on a trial and error basis, right? And so the first trial that we might do is take all of the predicates and lump them together into the same bucket S1. So wherever I see any of those predicates, I will instead write S1. It turns out that a couple of rules disappear after this transformation. And what you end up with magically is the program that computes SEC not just on that graph over there, but on every graph that you might find. Now, of course, it's nice in some way, this whole predicate unification process. There's a theorem we can prove that it strictly generalizes. But it might generalize in bad ways. And so we use some tricks from database systems that's to compute the provenance of tuples. And so we look at all of the bad tuples, we compute their provenance, and figure out ways of basically eliminating them. So for example, there's a graph. Here's a program that doesn't really quite compute SECs well. It ends up computing an undesirable tuple. The problem at this point, but just by looking at why this tuple SEC 3, 5, it says that 3 and 5 were in the same SEC, were generated, is there must be some issue in R1 and R4. And so that allows us to focus on which parts of the merge really caused the issue. And so this overall extrapolation process is kind of this CGIS-like structure. We started the original non-recursive program, normalize it, and then there's a back and forth between a data log solver, in this case Souffle, and a constraint solver Z3, where the constraint solver proposes a unification map, the data log solver checks it. If it goes wrong, then it computes the blame assignments, what part of the merge the unification was bad. And when it succeeds, then we have the final possibly recursive program. We evaluated this whole setup on a set of about 21 synthesis tasks. These covered a range of different recursive patterns, if you will. Transitive closure is an easy pattern to get examples or to get benchmarks out of. Intersection, strongly connected component, path from X to Y and a path from Y to X. And I already talked about monochromatic paths, so schema invention. So all of the benchmarks were some variations of these kinds of things. We compared them to 3 basically state-of-the-art baselines from inductive logic programming, from program synthesis, evolutionary search, and so on. 21 benchmarks. I have normalized the running time of Mobius to 1. And if you look at the other systems, it's, I forget the exact numbers, but really Mobius is clearly the fastest, right? By the way, notice that the y-axis is on a logarithmic scale, so it's really much faster than the remaining systems. Now, Mobius itself, like I said, started with a seed non-recursive synthesizer, and then it did something to it. So what's the overhead over EGS? Well, turns out not that much. In fact, even the benchmarks where we don't do very well, we can blame it on the seed synthesizer that we're working off of, not the algorithm that I just presented. Really, the question was, does it improve generalization? The short answer is yes, it does. These graphs look magical, but the fact is that Mobius just discovered the real query. EGS could not. And that's why you see the accuracy of EGS dropping off with larger test graphs. All right, so let me stop over here. I have run out of time, but really the conclusion of this talk was that I just presented a new algorithm to synthesize relational queries. And it can learn queries with recursive and invented predicates. The take-home message of the 5-minute summary of the algorithm is that you start with a seed non-recursive query, normalize it, iteratively unify predicates, use provenance to figure out what goes wrong, what went wrong in case something goes wrong. And the unified query is potentially recursive, and it gives you opportunities to generalize. We are able to learn several complex patterns of recursive queries, and without too much time overhead. Let me stop over here. I'll be happy to take any questions. Thank you.
Hi. This is a very interesting idea. I wanted to know, because you're learning the unruled version over perhaps smaller structures, do you have to choose which solution? I mean, there could be many things that could fit that, and so tons of effort has been spent on similar problems for re-ranking and things like that, right? So is that a problem here, and if not, why not?
It is. Okay. The short answer, the short version of the answer is that it is a problem. We use the Chomsky normal form. There's all kinds of non-determinism involved in actually constructing the Chomsky normal form. Whatever our implementation chose is what we chose. You are right. And in fact, it is a very interesting problem. So yes, we should talk about that offline.
Thanks for the talk. You talked about problems of correctness with extra tuples that you don't want, but is your algorithm complete?
So the completeness falls victim to the question that Aditya just mentioned, which is that if, so we are correct, okay, here the short version of correctness is that if there is a solution, we will always produce a solution. Is it the solution the user had in mind? We cannot guarantee that. But yes, the real failing is in my failure to answer his question about what if the Chomsky normal form was not chosen in the best possible way, or the seed non-recursive synthesizer gave us something spurious. The problem is always somebody else, not this algorithm.
Great. Let's thank Mukund one more time. Okay, so now we have Jocelyn Chen from UT Austin, and she's going to talk about data extraction via semantic regular expression synthesis.
So, hi everyone, I'm Jocelyn. Thanks for coming to my talk. Today I'm going to tell you about data extraction via semantic regular expression synthesis. This is joint work with Arko Banerjee, Chata Demirup, Graduate, and Ishol Delek. So first of all, let's start with talking about regex. So of course, as we all know, regex is everywhere, and it's very commonly applied in applications such as email validation, credit card matching, and also matching on HTML tags. However, there's one issue. As you can notice, all of these tasks focus on matching syntactic constraint. And the reason, let's look at why this might be potentially an issue by looking at a following task. So here I give you a data set where this data set describes a set of museum collection. And let's say user want to find all the European artists who were born before 20th century whose name contains Thomas. So if we think about how we achieve matching all the strings in this task, we can mainly divide into two types of way of mainly categorize in 2 ways. So first of all, we need to think about how do we parse the comma-separate string, because clearly this query is talking about the artist's bio column here. Also, we also want to think about how we match a string with the name Thomas. So I call these syntactic constraint. On the other side, we also have to think about which part of the string corresponds to name, how to find whether an artist is from Europe, and how do you check the birth year of an artist. And I call these semantic constraint. So if you think about using a regex to solve this task, I hope you can easily come to the conclusion that regex cannot easily solve this problem because there's a lack of support for semantic constraint. So in this work, I present SMORE, which stands for Semantic Regular Expression, that support matching a combination of syntactic and semantic constraint. And this is rely on the idea of extending regular expression with semantic matching, where regular expression, of course, as we all know, is very good with syntactic matching, and we have some semantic matching mechanism to handle semantic constraint. So how exactly does it work? The core idea here is to interpret sequence of characters with some semantic meaning. So in terms of what that means, let's look through 2 examples. So first of all, if we want to match a string that's described 20K, in traditional regex, you might want to write a program which is concatenate 2 with 40. In semantic regex, this is just a number of value 20K. If you want to match like person name, like Taylor Swift, Lionel Messi, in traditional regex, you might want to write a program which is 2 words that start with a capital letter, concatenated by space. In semantic regex, that's just going to be celebrity person name. So here, I show you the syntax about how you would like to potentially write it in our language. Here, let's unwrap like why the syntax looks like this a little bit more. So I call this a semantic matcher, and hopefully you realize it looks really like a refinement type. And where here, the tau represent a base type. In fact, in your language, we support any type of type as long as it has some semantic meaning, like restaurant, product name, processor, you name it. One additional semantic matcher is a base type that's annotated with some logical qualifier. So here, instead of supporting any type, we only support a set of building types, like person, organization, integer. And the way that logical qualifier works is that given a string S, we first interpret as an object of a specific type, and then we check whether this object satisfies a certain predicate. So we support stuff like check number ranges, check date and time values, and also check like location properties. So if you're curious about how exactly this is implemented, we use a range of constructs from daytime parser, entity matchers, and of course, large language models. So here, I already talked about the syntax for semantic matchers. For the rest of the semantic regex language, we have all the regular constructs as we normally see in regular expression, except the only thing is like the semantic matcher is a base case for the regex operator. So what exactly can this type of program can do? Suppose we want to match artist whose name contains Thomas. This is how we're going to write a semantic regex. So it's an intersection of a semantic constraint and a syntactic constraint, where the first constraint is semantics. It has to describe a person name. And also it has to, somewhere contain Thomas. If we want to match European artists who were born before 20th century in the context of our motivating example, so here we have a program that basically first talks about a country that's in Europe, concatenate with a comma, and a year that's less than 1900. So here I present you the language. However, there's one issue. Well, regex are hard to write. So as a second part of the talk, I'm going to talk about how we synthesize semantic regex from a few user-label positive and negative examples. Well, first of all, since we're having very few user-labeled positive examples, we have a couple challenges. For example, how do we generalize from a few, very few label examples, and how do we decide what semantic types to use? So one thing to emphasize here is that if you think from an enumerative synthesis perspective, since we support any type of base type, of course you cannot enumerate all possible base type in enumeration. So that's why this challenge comes from. Well, our key idea, again, is to use LLM to guide the synthesis procedure. So why using LLM, although everyone's using it, but let me try to convince you from analyzing the pros and cons of large language model. So on the pro side, large language model is very good at detecting text semantics. Well, because obviously this is what they are trained on. And it's also very good at generating regular expression because this have been all over the internet for years. On the other hand, it have a trouble doing precise reasoning that help us differentiate positive from negative examples. So by taking this idea, by relying on the pro side of our LLM, the first idea here, we're going to use LLM to generate what we call a typed regex sketch. So here I show you an example of typed regex sketch in the context of the motivating example. As you can see that this whole program looks pretty similar as like a regular expression, except the whole are annotated with some semantic type. So to handle the issue of how we differentiate positive from negative examples, we use program semantics to reason about how we differentiate. So let's take a detailed look at this synthesis workflow. We start with a set of positive and negative example provided by the user. We prompt the GPT and get some sketch, which we pass to the synthesizer. If we synthesize it successfully, we're all done. Otherwise, we go to the next sketch. First, let me elaborate how we do the sketch generation part. Well, we use prompting to generate the sketch. And specifically, we're asking it to summarize the structure of the positive examples. Because if user want to match something, there's probably some structure in the string that's shared in common. So here we give all the some sample example string as the positive example string. And here we give a label sketch. So in total, we provide 8 in-context example. And for each of the new tasks, we just append the query at the end of the prompt. And this is how we get the generated sketch. Once we have the sketch, we have to synthesize from the sketch. So since, as you can recall, every of our whole is annotated with some semantic type, and apparently we can do type-directed synthesis here. However, there's 2 issues. So first of all, since a lot of time, the structure of the string might be really large, we might have a lot of hosts in our sketch. So one thing is very inefficient to synthesize all hosts at once. And second, since our sketch is generated by the LLM, which have no guarantee whether the sketch will actually lead to something that's meaningful, the sketch generating may be really incorrect. So in response to this challenge, we actually propose a following synthesis workflow that decomposes this whole thing. So given a sketch, we first run a decomposition procedure so that we, instead of synthesize on the whole sketch, we're dividing into subproblems. And if the synthesis is failing with respect to a single sketch, we try to use the feedback from the synthesizer to do sketch repair. So how do we do this? The highlight of our synthesis technique is to decompose, do the decomposition and repair using the concept of over-approximation. Over-approximation is commonly used across many literature, but let's just revisit what exactly that is. So a over-approximation, basically of a sketch, accept every string that can be accepted by any program that can synthesize from the sketch. So in the context of our motivating example, if we have the following sketch, one simple way to generate the over-approximation is just to replace all the hosts with dot star, because dot star can always match everything that can be matched by the whole. So how do we use it to generate the decomposition? Well, basically all we're doing here is just run this over-approximation of the sketch over the positive examples. And we get the matched group string that matched by each of the single whole. And in this way, we actually obtain 4 subtasks where we can nicely decompose the positive example into 4 subtasks. And in this way, we can synthesize each whole pretty independently. So next, we're going to talk about how we use over-approximation for sketch repair. So let's look at a different sketch, where here, instead of like a year range, we have a year only. So this is a different sketch. By running the over-approximation, we obtain these 3 subtasks. And if you can take a detailed look at this, you realize the last column for the positive example is hard to synthesize. But here it is year, but in fact, here this is a year range. So the sketch generated is incorrect. The first step of doing sketch repair is through error localization. The way we're doing it is relying on the concept of over-approximation again, by replacing each of the whole with over-approximation. I keep running until we get a first error localization program that can accept all the positive examples. The more detail you can refer to or slide paper, but I'm just going to show you how we do the rest. So using this error localization program, we generate a repair specification where, as you can notice, it successfully locate the last hole to be the errored hole, and we also annotate with the set of positive examples. Again, we just prompt this single hole with a positive example to an LLM. We're able to obtain a new sketch, and you can see it's like a more refined version than the previous one we got. So that's all I'm going to talk about the technical part of the talk, and let's see how well it works. So specifically, we'll collect 50 tasks across 10 data sets in a various domains like sales, science, arts. For training, we propose 6 in total, positive and negative examples. And for testing, we have 20 separate test sets for each of the tasks for our synthesized program. So first part of evaluation is to compare our semantic regular expression against existing data automation baseline. And we compare against the following baseline, which the first is a traditional regular expression synthesizer. The second one is directly query, GPT 3.5, whether a string should be matched given the examples. And lastly, this is Flash GPT, which is extension of Flash wheel with GPT query ability. We evaluate in terms of F1 score and number of finished within 1 minute time limit. And you can see that in terms of both F1 score and number of finished, SMORE does outperform existing work, except for the ChatGPT execution because there's no synthesis required. Then next, let's look at how our synthesis technique compared to existing baseline. And here we compare against a ChatGPT synthesizer with respect to our semantic regular DSL, and a SMORE no sketch, which is a enumerated semantic regular synthesizer without sketch generation. And again, if you look at this graph, you can see that SMORE outperforms existing work as well in terms of the way it can synthesize or not. So in this talk, I present you SMORE, which is a language for supporting syntactic plus semantic string. And we also present you a synthesis workflow that can synthesize program for positive and negative examples. We do open source the code, so please try it out. And one more thing to add, I'm on the job market, so if you want to hire me or you're hiring, let me know. So yeah, that's it.
So thanks for the talk. So first I have like a clarification question because you mentioned you can have some sort of semantics. So in your template, like you have a regular expression that consists of 2 years. So can you say something like maybe the first year is earlier than the second year? So that is the kind of semantic constraint you can synthesize in this framework?
Yeah.
Okay, so then a follow-up question is, as far as I know, there are some existing language called ISLA, which can actually allows you to, you can say it's a first order logic over parse trees, which means you can have a context-free grammar. You can talking about, okay, what kind of relations we should have for these like non-terminal tokens, for example, non-terminal symbols and maybe some tokens, let's say. So do you think it's also possible to generate such, more expressive constraint because we know that regular is still very limited, let's say. And also that's why people make mistakes in validating email address because email is not regular. I mean, yes, so do you think that this kind of like expressive constraint can also be synthesized using these large language models?
Yeah, I don't see a particular reason why it cannot, I guess. And it really depends on, I feel like similar kind of technique I'm presenting here can also be applied to this. I'm not sure about the over-approximation part because our over-approximation is regular only. And you might have to think about other way to do over-approximation to decompose the task. But it's totally possible to support like, context-free language with semantic support and also synthesize from that. So I guess the answer is yes.
Okay, thanks.
Thanks for the talk, super interesting stuff. One thing that struck me when, the question that I have is exactly what you didn't talk about, which is how exactly the matching algorithm works. Because when I think about regexes, I think about big 10,000 line files. Can you speak about efficiency, economics, matching?
Well, that's a good question. So I guess, well, first of all, to be really honest, we did not apply this technique to a very large file because of, the way it works is, first of all, you're gonna do a pass over, so given you have the program, you already have a sense about what the semantics type are like, right? So basically you kind of use various matchers, you pass your input string and the type to various matchers and generate all the possible set of substring. And this is where, you kind of get the context for the matching to start performing. If you use GPT all the time, of course, you're going to go bankrupt, probably. But, which probably drive the need for, like, more specific type of tools, like, entity matchers, you can run it for free at this point. And it works pretty well on, like, stuff like person name or organization name. So I think that kind of require more better optimization in terms of engineering, but I would not consider as, like, a fundamental bottleneck. Does that make sense? Yeah.
Hi, so very short. So there's this model called symbolic automata, which has the similar structure. Have you looked into it? Because it seems like it's just regular expression with some alphabet theory, and you just have semantics, which is alphabet theory. So have you looked into symbolic automata, and do you know, like, is it similar, or is it something different?
I guess I'm not really sure what symbolic automata you're referring to. Is that kind of what you're kind of asking here?
It's basically an automata where you have alphabet theory. So you can say things like x greater than 2000 and whatever.
Oh, yeah, okay, yeah, sure. So I think, in this world I have not looked into, but I think there's a couple ways you can frame this type of stuff in different type of theory other than like just regular expression. I'm happy to talk about it offline. I think I have a reviewer who talk about clean algebra with test. It's also something along this line, I guess. So I'm happy to talk more about it offline.
Okay, thank you.
Yeah.
Let's thank Jocelyn one more time.
Sorry. Okay. Okay, this is. Okay, good afternoon. Okay, good afternoon, everyone. I'm Ethan from Peking University. I'm going to share with you about our recent work on synthesizing efficient memorization algorithms to solve combinatorial optimization problems. First, let me introduce the combinatorial optimization problems, short as COPs. COP is an important category of real-world problems. In general, it targets to find the best valid solution, where valid means that the solution should satisfy some user-provided constraints, and the best means that the solution should maximize a given objective function. For example, let's consider the classic 0-1 knapsack problem, where there are several items. Each item has a weight and a value. There is also a knapsack with a capacity limit. The goal is to choose a subset of items such that the total weight of the selected items does not exceed the capacity, and the total value of the selected items is maximized. Here we present a concrete example. There are 4 items whose weight and value is presented below. The capacity of the knapsack is 5, and the optimal solution is marked red. We can verify that the total weight of the red items is 5, which does not exceed the capacity of the knapsack, and we can find that the total value is 44, which reaches the maximum. So how to solve COPs? Maybe the first idea that comes into our mind is to apply exhaustive search, where we just try every solution and pick the best valid one. However, this is obviously too slow because the number of solutions is always tremendous. For example, let's consider the knapsack problem with n items. There would be 2 to the n solutions, which is exponentially large. To efficiently solve COPs, dynamic programming is a powerful and widely used technique. For 0-1 knapsack problem, its dynamic programming algorithm has a complexity n times c, where c is the capacity of the knapsack, which is much more efficient. Motivated by the importance of the combinatorial optimization problems and the dynamic programming algorithm, we propose a tool called SynMem that can automatically synthesize dynamic programming algorithms from logical description of COPs. At the input side, the logical description is written in a constraint modeling language, for example, Minizinc. In detail, the specification can be divided into 4 separate parts. First, the input part specifies all components to describe a problem instance. In the knapsack problem, we use n to represent the number of items, c to represent the capacity, and we use two arrays, weight and value, to represent the weight and value for each item. And in the right side, we show the parameter choice of a previously presented concrete example. Second, the solution part consists of all components to describe the solution. In the knapsack problem, we use the array P, where Pi represents whether to put the item I into the knapsack. If Pi equals 1, then we put the item I, and if Pi equals 0, then we does not put the item I. Third, in the constraint part, we impose constraints to the solution. In the knapsack problem, we make sure that the total weight of the selected items does not exceed the capacity C. And finally, in the objective function part, we will set up an objective function that maximizes the total value of the selected items. At the output side, we produce a top-down approach of dynamic programming, which is also termed as memoization algorithms. Generally, a memoization algorithm is in a recursive form. It decomposes a problem into several subproblems and recursively solves these subproblems. The key point that makes a memoization algorithm efficient is that during the recursively solving procedure, there are many pairs of subproblems that can be identified to be equivalent. For each equivalent class, we only need to solve one subproblem in this class, and the results of other subproblems in this class can be effectively reused. However, synthesizing a memoization algorithm is never easy. There are two major challenges here. The first, the memoization algorithms are always very large, and it is beyond the capability of the existing program synthesizers. And second, it will be very hard to verify whether such a large program is efficient or not. So there is an efficiency challenge. Our solution is that we propose a novel template of memoization algorithm that can tackle all previously proposed challenges. Moreover, our template is much more general than previous templates. And below, let's dive into some more details. To design a memorization algorithm, we need first to figure out the notion of subproblems. We find that the notion of subproblems can be extracted from the search tree of the exhaustive search. And in the right side, we present the search tree of the knapsack problem. It is organized in layers. The first layer is a root node. The second layer, we enumerate the value of P1. And in the third layer, we enumerate the value of P2. Below, we can see that there is actually a correspondence between the nodes in the search tree and the subproblem. At the root node, we can find that this subproblem is just identical to the original knapsack problem. Now suppose we have decided P1 to 0, and let's look at the red node. At this node of the search tree, since the value of P1 has been determined to 0, we can remove it from the solution part, and the solution part is just finding an assignment to the remaining P2, P3, P4 to Pn. And in the constraint part and the objective function part, we can replace P1 with its decided value 0. And we can find that this is exactly the COP that this subtree, the gray marked subtree, is trying to solve. Suppose we further decided P1 to be 1. Now the remaining task is further changed. We just need to decide the value of P3, P4 to Pn, and we can further replace the value of P2 to be 1 in the constraint part and in the objective function part. In general, every node in the search tree corresponds to a subproblem. By enumerating the value of a new variable, a parent subproblem can be split into two child subproblems, and the parent subproblem picks a better solution from two child subproblems. However, unfortunately, these subproblems cannot be reused, and let's see why. To reuse between two subproblems, in principle, we need to make sure that these subproblems will produce the same answer. In this work, we consider three natural conditions of the equivalence of subproblems that can guarantee the same answer. In detail, two subproblems are identified to be equivalent if they share the same solution part, that is, the same set of variables in the solution part, and they have equivalent objective functions and they have equivalent constraints. Let's check the first condition. It can be satisfied by many pairs of subproblems. we can see that as long as two subproblems are at the same level of the search tree, this condition can be satisfied. They will have the same solution part. However, the second condition is rarely satisfied, and let's see why. Let's just consider two sibling subproblems where they assign different values to the variable p1 and the other variables are still undetermined. We can see that the objective function depends on the value of p1. In the left side, we assign 0 to p1, and there would be a term called value1.0. And in the right side, we assign 1 to p1, so there would be a purple term called value1.1. And this is different, and this makes the objective function to be different. Indeed, different subproblems assign different values to the enumerated variables, and thus there is little chance to satisfy the condition on equivalent objective functions. So, to make the objective function independent with the enumerated variables, we introduce the local objective function, LOF, and replace the original objective function with the LOF. For knapsack, the LOF is the total value of the to-be-selected items. And we need to make sure that the replacement does not affect the answer, and it preserves the order of the solutions. After applying the LOF, the objective function of each subproblem become independent with the enumerated variables. So as long as two subproblems have the same solution part, they share equivalent objective function. Note that we also need an updating function for LOF to obtain the best solution of the parent subproblem from those of child subproblems. Finally, let's check the equivalent constraint condition. This condition can be generally checked via constraint solvers, but it would be very costly. Thus, we introduce a memoization partition function, MPF. We need to make sure that if two subproblems with the same solution part and they have the same MPF value, then they share this equivalent constraints over variables. For knapsack, this function is the total weight of the selected items. After applying MPF, we just need to check whether two subproblems have the same solution and that they have the same MPF value, which is much easier to check. We also need an updating function to efficiently obtain the MPF value of the child subproblem from the parent one. In summary, we have the following formula for memoization algorithms. We find that memoization algorithm is just the exhaustive search plus two functions, LOF, MPF, and together with their updating functions. Where the exhaustive search, they defines the notion of subproblems, and the LOF, MPF makes the subproblems to have more chances to reuse. As long as two subproblems have the same solution part and they have the same MPF value, they are equivalent and they can be reused. Thus, the number of the equivalent classes of this memoization algorithm is upper bounded by the number of variables times the range of the MPF. And finally, let's see why this template solves the two challenges proposed previously. First, we notice that each of the three parts is just a much smaller program to be synthesized. So we can design synthesizers to solve to solve each part. Second, we can control the efficiency of the memoization algorithm with the range of the MPF. By synthesizing an MPF with the smallest range, we can obtain the most efficient memoization algorithm, and thus we can solve the efficiency challenge. To implement a program synthesizer, we generate an exhaustive search from given templates. And to synthesize LOF and MPF, we propose a synthesis procedure that mixes the inductive and deductive methods. However, due to time limits, we just relegate these details to our paper, and please refer to our paper for details. Finally, the CMEM could be extended to decision problems and counting problems without any change. We evaluate our approach on 40 real-world combinatorial problems and that are collected from LeetCode and national-wide program competitions in China. And our benchmark consists of many classic and important combinatorial problems, and we find that our approach can solve 6 times problems more than previous approaches. That's all. Thank you.
Questions?
Hello.
Hi. I'm going to ask a question where I don't know if there is an answer, but I've written papers similar to this myself where we find kind of a nice domain where we can fit with program synthesis. And I see a lot of your examples, like similar to some stuff I worked on now is lead code and these basically problems that now lots of people are solving. And these days, if you ask ChatGPT to solve one of these problems, chances are it gives you a pretty good solution. So do you think there is a space, and I'm hoping that you give an answer so I can know the answer myself, but where like this type of techniques, are there domains that you thought about where this type of techniques will not be able to lose against LLMs and stuff like that? Does the answer make sense?
Sorry, pardon. Pardon?
Yeah, but I don't know if your experience working on these, if you found out things where you feel like there are problems where, are these problems common enough essentially that they will appear beyond problems that everybody solves like lead code or knapsack and so on?
Yeah, we solve problems from lead code.
Maybe I can answer this question. I'm the third author. So yes, we have tried ChatGPT, and so it's actually it's quite impressive. We can give the same millisync specification to it, and it will produce, if you get, say, the knapsack problem, it will produce a perfect answer with perfect explanation. So that's quite impressive because initially I expected it will only answer natural language queries, but we put millisync specification is still doing it quite well. But the interesting is that if we modify the specification a bit, say the weight is a sum of another two variables, so the value is, say, the difference between another two variables, then the ChatGPT just gave me totally random program that I cannot interpret the meaning. So I think the takeaway is that the ChatGPT actually have very good way of match programs, but if we want to adapt the programs, perhaps beyond some limit, it will not work well.
There's a domain that maybe you could try. I was wondering if you have done any sort of parsing problems, and because they are often dynamic programming problems. And in case you're not already aware, there's a programming language for dynamic programming algorithms called Dyna that you might want to look into and compare if you haven't seen that.
Dyna?
Yeah, D-Y-N-A, that's the name of the programming language.
This language can...
I'm not an expert in the language, but I'm just like...
Okay,
but I'm just wondering, the question is, have you tried parsing?
We don't try this language, and I think it would be a very great chance if we can try this in our ongoing work. Yeah.
So how do you determine that a problem is solved? Is it just that the memorization program is generated, or do you actually look at the efficiency of the generated memorization algorithm? So if you synthesize a memorization problem, you generate some code. Do you actually consider the efficiency of this code, like its running time in terms of the inputs?
We check the efficiency manually by ourselves, and we actually apply some inductive program synthesis approach, and the efficiency in the procedure is actually some concrete value, and we can just objective function to be minimized.
Okay, so I also wonder if there's a way to like tell the synthesizers that you want certain values, that you know that certain values will be smaller. For example, in knapsack, there's a capacity and there's the number of items. Can you guide it and say, hey, the capacity can be much larger than the number of items, and therefore the resulting algorithm, I want it to depend less on the capacity and maybe more on the number of items. Is it possible to incorporate that into your synthesizer?
Yeah, currently we don't, but I think that's possible. Yes, we can put some weights on the program, say that we just sort these programs. So currently we actually sort this program by their size. So the idea is that the larger the program, because it's a function, then the smaller its range. If you put more function after that, the range will become smaller. So then we prefer the large MPF function first. But then what you said, that we can put another weight function on that. By the complexity, we actually ensure all the generated program are pseudo-polynomial. And in that table, we have Just one column just says which of the problem we solved our solution reach the best complexity in theory. That's 31 out of 37 solutions. Okay.
And now we have Hitarth, and this is a Best Paper Award, so congratulations.
Thank you.
And he's going to talk about synthesizing polynomial programs.
All right, 2 more talks to go. So I'm Hitarth. I'll be presenting our work for synthesis of polynomial programs. It's with Amir Goharshedi, Fatemeh Mohammadi, and Harshad Mutwani. So this will be a fairly light talk. So let's start by thinking what is synthesis. So suppose you're given a template like this, that you have a precondition, you have a postcondition, and you have a program structure, if, then, else, but there is some part which is missing in it, so this part is missing. You give it to synthesizer, and its job is to somehow figure out what the value of this dude should be, and to give you a correct program. So these programs are supposed to be correct by construction. Okay. But if you give it a thing which can never be satisfied, then it should say that there's no solution. Okay. So what are polynomial programs? So they are imperative programs which look like this, like here, where everything is basically polynomial. So you have assignment to be polynomial, your guards are polynomial, and your pre and post condition are, of course, polynomial. So the first step would be that you can see that, OK, we can convert this into something we call polynomial transition system, which is simply, let's say, a control flow graph of this program. So then we have polynomial program template, which is what I showed you in the beginning, that you have some holes here. So you have like, it says you do something, but I don't know what invariant is. I don't know what the while condition is. And I don't know how to assign S. But I know that S is a polynomial, linear polynomial in INS. Here I know that invariant is, it consists of a quadratic polynomial in INS, at most quadratic. And then you have a post condition, which is, again, a polynomial expression. Now you can construct this transition system, which is we call polynomial program template, and you have these holes, which are where I substitute some symbolic terms. So for example, you see IS2. So I will just create a huge expression on INS, which is a quadratic polynomial, and every coefficient is a symbol. OK, cool. And now the job, basically, of synthesizer would be to figure out the values of all these t's such that this program is correct. OK? OK, so this is the overview of our tool called Polysynth, where you start by sketch PTS, and then you can convert it into a set of logical constraints, which is quite straightforward, which I'll talk about in a while. Then we want to eliminate the quantifier alternation, because these logical constraints have a quantifier alternation, and we convert it into something called quantifier-free fragment of nonlinear real arithmetic. And then you pass it to a SMT solver, a Q of n array solver, and then you get either your solution or no solution. OK. So how do we convert into sketch PTS to logical constraints? So here we use the standard invariant. We just use invariant for this. For example, you have this transition system from L0 to L1. You have some update, and then you have a guard, and then you go back, and then you update it, and then you have a negation of a guard, and then you go to this post condition, and then you can straightforward conversion to this set of constraint. And if you look at these constraints, they look like some polynomial imply another polynomial. OK. Now, what do we do now? So you have these, because you have a sketch PTS, so when you do the conversion, you actually get this kind of constraint, which have some symbolic coefficient. And the task is to solve all the constraints such that the symbolic variable, all the constraints become true. OK. So we know that now this is decidable by the theorem by Alfred Tarski, that because this theory of reals is decidable. But the main problem is that SMT solvers cannot handle when you have a quantifier alternation. And so the solution is that if we can somehow eliminate the quantifier alternation, then this problem could be tackled by SMT solver. So we'll talk about this approach where how we eliminate the quantifier alternation. And you might have seen a similar technique in the first session of this synthesis. So you have, depending on the degree of these polynomials, we use different theorems from algebraic geometry. So let me give you just intuition for them, so that you can because the theorems are anyway big and not very important. So you see that suppose you have something like, you know that this thing is positive and this thing is positive, and it should imply that x is positive, x is non-negative. So if this is non-negative, then every positive multiple of this is also non-negative. And every non-positive multiple of this is also non-negative. And if I can show you that lambda 1 times this thing plus lambda 2 times this thing is equal to x, with lambdas being positive, it's kind of if I can show you the actual value of lambdas, then it will give you a certificate that this is indeed true, this constraint is valid. So when you do this, you can actually just multiply lambdas on this side and simplify. You get a big polynomial equal to another polynomial, and this should be equal for all xy. And two polynomials are only equal when their coefficients are equal, so you just equate the coefficients on the both sides, and you get this set of constraint. And you can see that here there is no quantifier alternation. This is basically just existential quantifier. And this is Q of n array, and now we can use SMT solver to solve this. Okay. So, okay, let's leave this. This basically, Farkash lemma basically provides you a guarantee, and this has been done for linear program synthesis by people in 2004 by Srivastav and others. Now let's see, how do we deal with when we have nonlinear stuff? So which is more interesting. So suppose I have some polynomial f1, f2, and f3, which are all non-negative. So one intuition that you will have that every possible product of these things will also be non-negative. And this is what we call the monoid generated by this set of polynomial. So you take every possible multiplication up to a certain degree, and now if I can find a positive combination of these things, if there is any G which is a positive combination of these elements from monoid, then that will be also positive. So F will imply that G is also non-negative, okay? So I mess up the non-negative and positive, but just read non-negative. Okay, so here's an example. Like you have something like T0 x plus y is non-negative, x minus y is non-negative, and it implies x squared minus y squared is non-negative. So let's see some of the monoid element. So one of the monoid element would be this thing itself, which is here. Second element could be this one. And third element could be product of these two. And let's say this thing is equal to lambda 1 times this, lambda 2 times this, lambda 3 times this. And if I can write it like this, then basically I have, if I find actual value for lambdas such that I can write this, then this is a certificate that this constraint is actually true. Again, I do the same thing. I just equate both the coefficients. I simplify this, equate the coefficient on both sides, and I get a set of constraints which are quadratic. And this is, again, Q of n array. Now I can, again, use SMT solver to solve this, and again, SMT solvers are fast on this thing compared to when we have alternation. OK, so this is there's a constraint here which I want to mention, that the premise that you have here, which is some conjunction of polynomial, this has to be compact, which means that it has to be bounded, and it has to be closed. To deal with this, what you can do is that, because in real programs, your variables are anyway bounded, so you can actually artificially add some bounds on every variable, and then you will satisfy the constraint of compactness. And yeah, so that's why we can apply this, and this gives us a completeness for this kind of expression. But remember that this only works when your polynomial in the left-hand side of the implication are linear, and the right-hand side is nonlinear. So what do we do when we have nonlinear stuff on both the sides of the constraint? So for that, let's see some example. Let's say I want to look at this particular constraint. And I can write this x. OK, so there is a typo here. OK, so I can write this x times y minus 1 squared plus xy is equal to xy squared plus 1. So this x is positive because of the, that's my assumption. And then xy is positive. OK, forget this. Just look at this. Xy is positive. And then if I multiply this x with the sum of a square, then that will be positive. So if this thing has to be positive if x and xy are positive. And the reason for that is because I'm only multiplying by SOS, and sum of squares or squares are positive by default. OK, so here's another example. Like, OK, OK, let me go through it. So x plus y cubed is non-negative. Ty is non-negative, implies 3x is non-negative. So I will write some sum of a square here, and then some sum of a square here. So every positive number is a square in itself, so it's fine. So if I can write 3x as this combination, then this is a certificate that this constraint is valid. And I can reduce this again by comparing both the side of coefficient, that this becomes a Q of an array, and then when I solve it, I get some values, and then I can put it back and check that it's indeed correct. It's indeed correct. So this is how you can eliminate the quantifier alternation and reduce it to Q of an array. Okay, so this also has some technical constraint that you should have this to be compact, but again, as I said, we can always artificially add constraint to make it compact. Okay, so one thing that you might have noticed that this sum of a square thing, I didn't talk about how do we actually handle this sum of a square. So what we do is that we have to construct a general template of a SOS, which is sum of a square. And the way we do it is using some basic linear algebra theorems that if you have a polynomial which is SOS of degree 2D, then it should be, there should exist a positive semi-definite matrix Q such that your polynomial is nothing but m times Q times mt, where m is a set of vector of monomials of this format. And if I can write it like this, then it's, if this is a positive semi-definite matrix, then it's guaranteed to be an SOS. So, but a matrix is only positive semi-definite if it can have this sort of decomposition that you can write it as like L times LT, where L is a lower triangular matrix. So for example, if D is equal to 1, then and M is equal to 1xy. So I'm trying to find a SOS of degree 2 on xy. Then I can construct this matrix L matrix, and then I can multiply this whole thing, and whatever I get, that will always be a SOS. That follows from these theorems. Okay, so that's the main thing that you, so what you do ultimately is that you take this is the whole algorithm, you take the symbolic, you take your PTS, and then you retrieve the constraint from it, and then you apply either the Farkas-Lemma, Handelman's theorem, or Putinar's Stalinzatz over some degree D, where you select a degree D. So where this degree D is coming from is that, if you remember that in Handelman, I told you that this monoid can be arbitrarily large, but you want to limit it to certain degrees. So suppose you choose a degree 2, then you will only look at product of degree, like product of two polynomial. So f1 is square, f2 is square, f3 is square, f1, f2, f1, f3, and so on. And similarly, in Putinar's positive Stalinzatz, you have this sum of a square, and you have a parametric degree for that too. Okay, so you use the degree D, and then you try to solve it, the QC, the quadratic constraint that you obtain after applying this using SMT solver. If the solver says unset, then you just know that there's no solution for parameter D, and if it is set, then you can construct the program. So you have to try this for degree, increase the degree arbitrarily, like as long as there's a solution, you will find it if you keep increasing the degree step by step. Okay, so these are some experiments that we did. You have so just look at the green arrows, like green tick marks. That's it. So this is Sketch. So most of the program are not supported by Sketch or don't work, or it gives the wrong answer, which is WA. Rosette is another synthesizer based on Racket, where it works on some of the things, but not on all the benchmark that we had. And we also use direct Z3, so we just pass it to SMT solver Z3. And this is our approach. So we see that some of the benchmarks are not supported because these benchmarks required either integer reasoning or they had modulus operator and things like that, because we can only handle polynomials, so we couldn't handle those kind of benchmarks. And yeah, so we presented this algorithm which is sound and semi-complete. Semi-complete because it depends on degree D. For template with synthesis of polymer programs. And this algorithm is parameterized by the degree of the monoid in Handelman's theorem and the degree of SOS template used in the positive Stalinzatz. Okay. So the code is available on GitHub. It's called Polysynth. Thank you.
Sorry, very silly question. I didn't understand, what is the specification you synthesize with respect to?
So okay, there are these precondition and postcondition, which are just polynomial inequality, like conjunction of polynomial inequalities.
But you don't guarantee termination.
We don't guarantee what?
Termination.
Termination of algorithm?
Like you guarantee the pre-post holds, but not that the program will terminate another.
Yes, correct. Good. Yeah, good point. Yeah, we don't guarantee termination because but if we add the ranking function, then we can of course guarantee it if we put a ranking function in the invariant. and then try to synthesize it. But yeah, we don't try to get termination of the program, not the algorithm. The algorithm will terminate, but
but otherwise you can prove call-outs or anything,
Yeah.
any conjecture. Okay.
Yeah. Thanks.
Yeah, I'm wondering if your approach can support data structures, like some list.
So data lists are not polynomial, unfortunately, if you have arbitrary size. But if you have, of course, a finite size, then you can blast it, like bit blast it. In bit factor you do it. So you can just give everything a variable name, and then you can try to do it. But that will increase the number of variable a lot, and then...
Oh, but then you need to know its size in advance.
Yeah, so yeah, we cannot handle list in general, correct.
So I'm wondering, like, how is the scalability of the approach? Because in the end, you still have to call SMT solvers, and it seems that you have some like optimizations on that. So do you have some results that shows the scalability, and also like what is the largest like program you have in the benchmark that you can?
So the funny thing about this the SMT solvers is that you cannot, even if the thing is very small, it might just be stuck forever. So it's not the size which is a factor, but it's about some sort of internal complexity that these things have.
Yeah, I agree.
So yeah, so I don't think the size is actually a parameter, but yeah, if you think about the size visible, then maybe like 20, 30 lines.
Yeah, but how about like the size of the problem? Like, because in practice, well, maybe you have like hundreds of lines of code or thousands of lines of code. So like this kind of scale. So do you have some numbers or distributions?
The programs that we use here, they were all like up to 20 lines of code in our own language, which we, like a DSL that we invented. But I think the good comparison would be that where does Z3 fails and V pass? That's a good comparison because that tells you the problem is hard if you just put it like a constraint. But if you do the quantify elimination, then it succeeds, the Z3 succeeds. So it means that this approach is at least improving the state of art.
Okay, thank you.
Sorry, I have one question. Oh, sorry, go ahead, it's fine.
Thanks. So thanks for the nice talk. I have a question whether you have ever looked into the special case where you only have bilinear constraints in your system of constraints to be solved.
So what would be a bilinear constraint? I'm not sure.
So you have parameters, and then all the constraints are, let's say, if you have a constraint of the form P times Q, both of them are parameters, and it is linear in P and linear in Q.
It's quadratic, you mean? Is that what you mean?
Yeah, you can also say quadratic, but not highly nonlinear. I mean, in this special case, I think there are some existing works.
Sorry, I'm not sure I can answer the question right now, so maybe we can talk later. Yeah.
Okay, sure.
So the final talk of the session is modular component-based quantum circuit synthesis, and we have Chan-Gu Kang presenting the work.
Thank you. So let me begin. Hi, everyone. My name is Chan-Gu Kang from Korea University. I will be presenting our research, modular component-based quantum circuit synthesis. This is a joint work with Hakjuo, also from Korea University. So as the title suggests, our research is about the synthesis of quantum circuits. So let me first introduce some concepts of it. Although the circuits are the lowest level of programs, we focus on the synthesizing circuits. This is because we believe that circuits are sufficient in the early days of quantum computing. So for example, consider the Shor's integer factoring algorithm, which is one of the well-known applications of quantum computing, as it can be used for breaking the well-known RSA cryptos. It possesses a quantum complex structure and is in a non-trivial scale, and yet, just like this diagram shows, it is enough to be described by the circuits. So here's more detail in quantum circuits. Quantum circuits are composed in qubits, which is a quantum version of bits, and quantum gates. In this diagram, wires represent a physical placement of qubits, and some symbols on wires. For example, here a box state represents the quantum gate named Hadamard, and a vertical line that bridges two wires with some circles on it represents the gate named CNOT. And then its computation is basically a linear algebra. Each qubit holds its state value as a vector. For example, the symbol 00 cat, and often it is expressed in a cat. And for example, the symbol 00 cat represents the four-dimensional vector where the first element is 1 and the rest of elements are 0. Then naturally following, a quantum gate becomes a matrix transforming the state vectors. So for this example of circuit diagram, when input state vector is provided as 0, 0 cat, this sequential quantum gate produces another state vector where 0, 0 cat and 1, 1 cat is proposed, which is evaluated to be the vector on the rightmost. And we found such quantum programming is hard. Indeed, this case of stack exchange question confirms the difficulty. The questioner asks for a circuit that maps 1, 0, 0 cat to a state vector where 3, 3, 0 cat and 3, 1 cat is proposed, and the solution circuit turns out to be the right there. I guess it seems like a relatively simple circuit, but this case of question here shows that quantum programming is hard, even for the simple cases. We figured that this is maybe because the linear algebraic nature of quantum computing, where the basic operations are matrix, which is definitely non-intuitive to the manual computation. So here, our basic goal becomes to give an automatic synthesis of quantum circuits for the programmers. And here's another example, which is even more non-trivial. Consider a synthesis of 3-qubit quantum-free transformation. It is a key part in many practical quantum algorithms, including the Schwartz algorithm. And the input-output specification for QFT should be given as this, which I guess is definitely non-trivial to program. And also, there were cases of question from circuit programmers asking for the implementation of QFT. This supports the difficulty of the problem. And indeed, actually, there already is a technique that produces a quantum circuit when I/O specification is provided. However, we would like to say such techniques are presented to be compilers, rather as a mean of generating only machine-readable circuit by fixed lower-level gates that only computer machine can directly process. So, for example, consider a gate named U0, U3, and C0, which becomes one of the choices for such low-level gate sets. When the existing compilers is fed by I/O specification, for example, the I/O spec of 3-qubit QFT, the compiler gives a circuit, but barely compressive one, as it is inflexibly composed by a massive amount of low-level gate sets. So this fact gives one of the necessity of our problem, which is component-based quantum circuit synthesis. Basically, we assume user specify input-output specification, and also we assume user specifies component gates that will be used as an ingredient in a circuit construction. Note that ours adopts the component case to be any, so especially when specifying the component gate to be high level or something that reflects the programmer's mind, then our synthesizer produces a circuit written in component case, which will be fairly readable to the programmers, which is contrast to the result from the compilers appeared in the previous slide. And by the way, our technique successfully synthesizes this QFT circuit in 220 seconds, while the baseline, which will be explained later, produces timeout. So here's our approach to the problem. Although the domain is new, we follow the typical method for the program synthesis, which is to do search-based. The most simplest method will be enumerating the space of quantum circuit by building up the circuits with component gates one by one. But for ours, we take a little variant version. Instead of enumeration by single gate operations, we conduct the enumeration by appending modules. Here for modules, it's a simple concept. We mean a collection of component gate operations. So for example, in this diagram, each orange boxed sub-circuit represents the module. And by this module approach, we are taking a big step in each stage of synthesis and expect to reach the solution circuit in a faster step. But of course, our choice of this modular approach does not give inherent speed up in search. What's most important is the guidance of modules to append. And the method of guidance becomes our key idea in this research. Our idea is phrased in saying, filling the attribute difference. So for explanation, consider our I/O specification as pair of in-cat and out-cat. Especially, we color the out-cat as blue, and as our object is to prepare the out-cat, we can just simply say it as an object state vector. Here, SB is a short name of the state vector. And also, a green colored cat will represent the output state vector of some quantum circuit QC appear during the synthesis. Simply saying, since green cat represents the current status of a circuit under the construction, we can simply say as a current state vector. Then we characterize the difference in attribute level between those object state vector and the current state vector. Then we guide to append a module that fills the difference between them. So more concretely, if a module M transforms the current state vector to be same with the object state vector in an attribute level, then we append the M. So, and in contrast, for another module M prime, if it does not transform the current state vector to be same with the object state vector in attribute, we print out the M prime. So we will dive into the simple working example that shows how our idea applies. Consider an example where the goal is to synthesize a circuit that maps 1, 0, 0 cat and to another state vector where 3, 0 cats and 3, 1 cat is proposed. The specified components gate is H and C naught, which means that we will be appending some modules that is composed by H and C naught. Initially, the synthesis starts off with a blank circuit, and its action is identity function, mapping the input 001 cat, the 100 cat to 100 cat, the same one. For the blue-colored object state vector, through the calculation, we can check that object state vector is entangled. Here, entangled is some terminology in quantum physics, but mathematically, we can understand it as inseparability by tensor products. And in contrast, output state vector of a current quantum circuit is unentangled. Hereby, we derive the attribute difference between them as an entanglement. Then our guidance goal becomes to append the module that fills the entanglement difference. We prepare the candidate modules for one that is likely to fill the current entanglement difference, although the detailed method will be skipped for now. But anyway, let's see how each module transforms the current state vector and decide which to append. The M1 prime module gives a state vector which is not entangled. So we can say that M1 prime does not fill the entanglement gap. So we decide not to append the M1 prime to pruning out it. And in contrast, the M1 module transforms the current state vector to be entangled, being same as the object state vector in attribute. So as we can say, M1 fills the difference of entanglement. We append the M1 in the synthesis. So as a next stage, we may start our synthesis from the circuit with M1 appended, obtained from the previous stage. So in this stage, considering the action of the current circuit, we can check that current state vector is different in sign of coefficient compared to the object state vector. And by some quantum physics reason, we call it as a difference in relative pace, or shortly just a pace. Then the guidance goal becomes to append a module that fills the pace difference. And also in this case, we prepare the modules that is likely to fill the pace difference, such as M2 and M2 prime. But here, M2 actually switches the minus sign to the plus sign, thereby reaching to the object state vector. So just by coincidence, we may get to the solution circuit before the pruning modules. So far, this was all about our method for the guidance. Now we will convey the evaluation result of our synthesis algorithm. We prepare 17 non-trivial synthesis problems from sources like textbooks and stacking questions in the internet. And we give two other settings as major comparison target. We set the baseline as the most naive approach, which is to enumerate by gate operation, explained just ago. And also, to check the effectiveness in guidance, we also compare with the modular approach. We also compare with our modular approach without the difference filling guidance. So here's a table. In overall, our approach could achieve effectiveness compared to other two settings. First, while the two other settings solved the 10 and 14 problems out of 17, ours could solve 16 problems within time. So also in terms of speed, ours could achieve faster synthesis time. Compared to the baseline, in average, ours achieved 6.6 times faster in synthesis time. And compared to our no-prune, which is our version of no guidance, we achieved a 7.1 faster synthesis time, which implies that our guidance filling idea was effective enough. And also, here we show the result of a circuit presentation by our component space and the one from the existing technique, which is to be a compiler. Since the component gain were specified to be high level, enough high level, we could achieve pretty neat representations, while by the compiler tool, it only managed to produce an incomprehensible one. So again, this supports the value of component-based synthesis. So actually, here's the summary. At last, here's the summary. We proposed a problem to synthesize a circuit with I/O specification, and the user provided component gates. We took a search-based approach, and our key idea was to characterize the attribute difference and guide to append modules that fill such attribute difference. And personally, more importantly, several features works are established from this study. The most direct feature work will be extending our work to a language-based quantum programming, which is written in, for example, the Silk, and the Qiskit, which is embedded in the Python. And also, we can apply our synthesis idea to other synthesis problems, for example, circuit optimization. So this is it, and thank you for listening.
Hi, thanks for your nice talk. The input-output specification, do you only specify one in and output, or can you also specify multiple ones?
There is some limitation. It could be one or multiple, but only through the explanation. Only in the working example, I suppose there is one single I/O specification.
Yeah, that's why I ask. I assumed it already. But when you have different in and output pairs, you could have different attributes.
Oh, that's true. Yeah, that's
and
true.
how do you choose between them? Do you have some heuristic or?
I managed to have a board so of course, if there's a multiple I/O specification, there could be multiple kinds of attribute differences. But I chose one of the most frequent differences as just a simple heuristic. But yeah, that's a simple heuristic. But anyway, it works. So
thanks.
So I have one question. So it seems like you expect the user to give you the components.
Yes.
Right? And is that easy in practice, or are there? Did you ever face any issues with?
Well, I like to say it can be easy, but in practice, at least not for every problem of synthesis, it may not be easy. So actually, this becomes one of the future directions that we have to resolve. For example, assuming that component gates include something that is not proper. So yeah, that remains as an issue in this research.
And like, what is the largest circuit that you were able to generate?
Oh, in terms of qubit size, the largest one was actually 4. I know it's a little bit disappointingly small, but yeah, it's small. But I guess it may be practical enough for the early days of quantum computer, because still in these early days of quantum computing, the perfect qubits are only about 7, or only about the 3 or 4 qubits. So yeah, but still we have to resolve the scalability. Yes.
Thanks. Other questions? All right, well, let's thank the speaker one more time. All right, thanks everyone for joining the synthesis session.
조금 빨랐긴 했어가지고.
네, 안 빨랐어요. 오히려 너무 빨랐는데 지금 괜찮았어. 아직 괜찮았어. 잘했다. 야, 지문이 진짜 맛있게 나와. 잘했어. 나는 좋았어.
Okay, should I be speaking into the mic?
Yeah, and he should be able to hear you.
Oh. Hello. Okay, hold like this, closer. Okay, but if I stand over here, it should sound better. All right. Testing, 1, 2. Can you hear us? Okay. I am opening Discord. Now try. Okay, Yossi, can you hear us? Hello, testing, 1, 2. Yep, desktop from other side. Hello. Ah, hello? Okay, Conrad is Evie. Okay. So what's the correct stage? Splash, oops, the stage. All right, it says Yossi is sharing screen, so he's still on the wrong stage. Yep. I just DM'd him. It says at the top that he's sharing screen, but I think he's in the wrong stage. Yeah. So I sent him a message that says join Splash Oopsla. I'll check email now.
We can also send him the link to
Testing.
the stage. So if you scroll down, oops, no, a bit. There you go. And cancel. If you go back, now long tap on the stage. No, you were right. Just long tap on the stage. Yeah, and then it'll show you copy link.
Testing, testing.
Okay, yep.
Okay, now it's good.
And let me check email too. I'll try to send it through there. Oh. You don't know where he is. Okay. Wrong stage still. Okay. Maybe he got up to stretch or something. So I sent him email with the link. I sent direct message. I'll go on to that Splashy stage. Yeah, we're missing. Is he still in the wrong state? We have a remote person. Oh, he's stuck in Israel. Yep, there was not supposed to be anybody remote for this OOPSLA, so this is last minute. I think it will work, he's just on the wrong Discord channel. He's live, just in the wrong place. Oh. I can't join SPLASH'. Okay, good. He's left SPLASH'. He's in SPLASH OOPSLA. Awesome. Okay, hello? Hello? Oh.
Can you hear me?
You can hear Yossi? Hey, Yossi, can you do some more testing? Speak a few words, testing 1, 2. Also, please start your video. Awesome. Okay, we're not hearing anything. Still no audio. We do see PowerPoint.
Anyone there?
Wait, did you speak?
Can you hear me now?
Yes.
I'm trying to speak now.
Okay, awesome. We can hear you. It's a little bit quiet. Can we turn up the volume here? Okay. Okay, keep talking so that we can adjust the volume. Yossi, can you say a few more words?
I'm trying to check something here.
Okay. That's pretty good volume. Okay.
Can
Now, whenever you're ready, share the slides or put it in presentation mode. Right now, we see the whole PowerPoint. When it turns 4, can you step outside and clap and say the next session is starting?
Yeah, I can go, yeah.
Can you hear me now?
Yes. Now, can he see anything? No. Can he see? Does he have any window on the room? No. Okay. Okay.
No, I cannot hear you guys for some reason.
Okay, but that's fine. No, you'll turn that on. You tested that.
Can you speak now, please?
What's that? So
I
we're about
changed the
ready to.
setting. If you hear me, please try to speak.
Yes, I can hear you. So people are still filing in. We'll start in about 1 minute. And then after the talk, you should be able to hear questions through another microphone in this room. Well, let's just communicate with him over chat. So let him know we're going to start in about 1 minute. And then once I'm done, just say go.
As long as you can hear me, I do not need to hear the audience.
Okay, yeah, let's just start and tell him to go in 1 minute. Okay, welcome everyone to the DSL session. We have got a packed session with 6 talks for you. Our first talk, unfortunately, is by a pair of authors whose travel plans were canceled at the last minute. So we have one remote talk at this UPSLA, and it is happening right now. So, Yossi, please take it away.
Okay, I'm going to start the presentation now. Okay, so welcome everyone. I'm afraid we are in a very awkward situation in which I, for some reason, cannot hear the audience, but the audience is supposedly hearing me. So what I will be doing is I will be going back and forth as I present from the chat to the main presentation. Okay. So you can pretend that this is a recording. And the topic of my presentation is fluent APIs in functional languages. This work was done by Ori Roth and Yossi Gil, and notice the order of the authors is not alphabetical, and this is not randomly, this is by decision. We both come from the Department of Computer Science at the Technion. That's a photograph of the building. And let me introduce to you Captain Ori Roth. Captain Ori Roth is my PhD student, and he is a full-time Army officer. And I haven't seen him or heard from him ever since the war started. You can see some of the fireworks we have here. And I tried myself to make it to Lisbon. Some of the flights were canceled. So let me try to deliver the presentation to the best of my ability in this awkward situation that we are in. Okay, since Ori is not here, I'm going to try to suggest a different title to our work. Our work should be advertised as pick any functional language you like, and we will show you how to embed in it any DSL you like. But by showing you, I mean that you have to go into the details, into the deep logics and hence the lambda calculus that are beyond the implementation. But we don't have a tool to offer you, not the level that you can use right away. But in principle, this work allows you to take any domain-specific language and embed it in your favorite functional language. Okay, if you want to view this presentation, this contribution in view of languages, this could be described as how F# is better than C#. Well, are there any F# people who are F# enthusiastics in the audience? Please respond in the chat. I'm sharing the wrong screen. I'm sorry. Wow. Okay. Am I on the right screen now? Is it okay now? Okay. I'll just flip through if it's okay. I'll stick to edit mode. That's good enough. Don't worry about that. Okay? Can I continue my presentation? So quickly, the paper is done by Ori Roth and myself, and this is Ori Roth. I suggested that the alternative title of our work would be the extension of your favorite programming language, functional programming language, to embed your favorite DSL. and I was discussing the issue of how F sharp is better than C sharp. And then I went to check whether the people in the audience who are enthusiastic of of F sharp, because I'm not an F sharp expert, and I would appreciate the help. If anyone in the audience is an F sharp enthusiast, please raise their hand or feel free to interrupt. Okay. So going back to the presentation. What we found in this research is that F sharp, and F sharp is just an example, is a challenge for embedding languages in it. We thought that it was impossible, and let me show you what we found. Okay. So let's start with this example, which basically summarizes the contribution of our work. So suppose you have a web page, and this is the text of the web page, and you want to take this web page and assign it as is into some value or some variable in your favorite programming language. In our example, the favorite programming language was standard ML. And the embedding was done in this way. We needed this little bit of syntax here, and this little bit of syntax here to allow the embedding. And other than that, we used operator overloading, and the syntax of standard ML as it is, to embed in it our HTML code. So this is the actual code as it's been written, and if you take it and you feed it to your favorite standard ML compiler, then it would run, it would compile if and only if the syntax here is correct. Of course, for this to happen, you'd have to load the library that we generated manually. But then if you do that, you'd have something which is quite fantastic. You'd have here the property that the type checking of standard ML would allow you to check the structure of this HTML document, meaning that it begins with HTML and ends with HTML, and body is within HTML. And furthermore, it allows you, or the type checker of standard ML would check that in each and every row, there are exactly the same number of columns. And this is quite remarkable because this is not context-free language. Okay, now let me remind you of LINQ. This is a very successful example of DSL embedding. And here's an example how this is being done in C#. In C#, you can write something like that. This is the code that you write, and you write the code. You write this C# code, and then you can begin writing something that looks like SQL. It's a variant of SQL. And there is a little bit of C# magic that translates that, what you've written here, into C# code. And the whole magic here ends with this semicolon. Okay, so that means that LINQ does something very similar to what we do. Okay, Few words about LINQ. The host language is C#. The embedded DSL is SQL. It's well integrated into C#. It is so well embedded into C# that you can extend and change the implementation of LINQ if you wanted to. The implementation, as I said, is by language extension, and SQL support is built in. Other DSLs, it's not clear how much you can do. But the fundamental property of LINQ is that it relies into translation into C# code. And this C# code is written in what is known as the Fluent API. And this Fluent API relies on its turn on a property called overloading, language property. Okay, so having seen what's going on in LINQ, let's discuss the story of query expressions in F#. So as I said in the beginning of my presentation, F# is advertised as being better than C#. And the promotion of F# requires embedding of DSLs. Specifically, the people who are prophets, advocates of F# really want to have F# to have something similar to LINQ. However, due to the fact that F# is a functional language, they cannot do that, and they had to do an extension which is very different from the extension of LINQ to C# in order to be able to embed DSL code in F#. However, in principle, you could have used our technique. I haven't actually tested the code. I'm not an F# practitioner. You could have done the same thing that's being done in SML in F#, because you rely on two things: the ability to invent your own operators, so you can invent your own syntax, and the type system, which makes it possible to embed whatever programming language that you wanted in F#. So presumably, F# code with the appropriate library written in the same fashion as described in our paper would be able to embed not only our HTML example, but also SQL or variant of SQL that you do. Okay, so what was the problem in taking the C# approach and implementing it in F#? The thing is the following. The magic here that we see in embedding SQL code within C# is realized by what is called Fluent API. So there's a little magic for us to this to this, and from that point, from this point on, C# carries on with its own compilation process. So, and the syntax here is Fluent API. You start with an object, you apply a method to it, then you apply another method, and here, when you iterate over the collection, you again apply a method, and you can apply more methods, etc. So, Fluent API fundamentally depends on the fact that you can interpret the same identifier in different meanings. So, for example, if you had a file object with a simple Fluent API, then you would want to allow sequences such as open, read, close, but you wouldn't want to allow close on a file that hasn't been opened, and you won't allow open to be applied twice before the file being closed to that, which means that open is sometimes okay and sometimes it is not okay, and it depends on the type of the receiver object. In order to do Fluent API, you have to rely on overload. So I see that I'm running out of time, so let me proceed quickly. Fluent programming languages rely on Hindley-Miller type systems. Hindley-Miller type systems do not admit overloading. This is what makes it possible to have everything clean, elegant, and still very expressive. If you had allowed overloading, this wouldn't have worked. So we tried doing that, and we found, to our surprise, the following result. Not only that we can do in Hindley-Miller type system the same languages that we can do in using overloading and procedural language, object-oriented languages separately. We can do more than this. We can do more than context-free language. And the trick here is simple. This was the difficulty. The difficulty was that there is not much you can do with the Hindley-Miller type system. There is no kind of computation that you can do that. You have types, and you can build types of types, and you can check whether the type matches, the type of the argument matches the type of the parameter. But that's it. You cannot do any computation. This reminds us of the lambda calculus. In lambda calculus, the pure lambda calculus, there's nothing that you can do. You can just have functions that call other functions. So the trick that worked was to use Church Boolean.
Okay, I'm sorry to stop this short, but we need to move on to the
Well,
next talk
Church
in the
Boolean.
session. So let's
Church
thank
Boolean
our
is very
speaker.
simple. Church Boolean are functions that take return either the first
So
or the
again, this
second
first
argument.
paper showed how to
You
encode
can
something
define
called
functions like
Fluent
that
API, which
in
is easy to do in
every
an object-oriented
programming
language
language, in
inside
every
of a
functional
functional
program.
language. So I encourage you to
And
check
with
out
this
the paper and
function,
email the authors if you have
and
questions.
with this trick,
Next
based
up, we
on
have
this,
Oak, who's going
I
to tell us
won't go
about
into
what's
the
new
details
with
here,
pretty
so
printers.
I'm running out of time. We were able to achieve that. The details are in the
Hi,
paper.
I'm Saraway Oak. Today, in this talk, I will present our new pretty printer, a pretty expressive pretty printer. So let's get started. Pretty printers takes as input a document in a printing language and an optimality objective parameter. For most printers, this is usually a quantity known as a page width limit, which is the maximum number of characters that each line should can have. And then it outputs an optimal layout. More elaborately, the document encodes a set of layouts that the user wishes to express. And the printer's job is that it should read this objective parameter and combine that with the optimality objective to pick the optimal layout and then present that as to users. As an example, let's say that a document encodes these two layouts. They are both function application, but they are styled differently. One is in the horizontal style, and the other is in the vertical style. So let's say with the width limit, page width limit of 15, with the optimality objective of trying to avoid overflow over the page width limit whenever possible, and then try to minimize the number of lines. Well, in this case, that creates that line, the page width limit. And we can see that both layouts are under the page width limit. And so the one with the minimal number of lines, which is the first layout, would be the optimal one. But let's say that if I change the page width limit to 10, in this case, the first layout has an overflow, but the second layout does not have an overflow. And so the second layout is the optimal one. Now, there are so many pretty printers in the literature. Why? Why isn't there just only one pretty printer? Well, the answer is that different pretty printers make different trade-offs in the expressiveness of the printing language, optimality objective, and the performance. In particular, we can group these
printers in the literature into two categories. We call the first one the traditional printers, and the second one the arbitrary choice printers. The characteristics of these printers are as follows. The traditional printers has poor expressiveness. Relatively, it has poor optimality objective, but it has really great performance. On the other hand, the arbitrary choice printers has an okay expressiveness. It has an okay optimality objective, but it has poor performance. And that's a bummer because 2 years ago, I wanted to create a code formatter for Racket source code. And so I emailed my co-author, Justin, asking for his advice. And he basically said that, yeah, you need to pick one of the printer from these two categories, and you need to pick like which one you want to be bad about. And so natural question is that, can we do better, right? And in particular, I want something like this. I want a printer that has good expressiveness, has good optimality objective, and ideally I want good performance as well, but if we cannot achieve that, then reasonable performance is kind of like the next best thing that I want. And just to give you a hint, yes, and that is our printer Pi-E that we will talk about today. The main challenge, of course, is that there are tension in the expressiveness, optimality objective, and the performance, right? And so how can we make it work? Well, let's try to break it down. We want good expressiveness. And so let's take a look at the existing printers and see what we can learn from them. The traditional printers target a printing language that is called the traditional printing language, which has poor expressiveness. And this is partly because it cannot express layouts that differ in more than just white space, which does occur in practice. For example, in Python, we have this kind of code, right? We may wish that we can create a document to encode these two layouts, where one of them is a string concatenation in the horizontal style, and the other is in the vertical style. But Python mandates that if you write the string concatenation vertically, you need to put parentheses around it. But this extra pair of parentheses cannot be expressed in the traditional printing language. All layouts must be the same modulo white spaces in the traditional printing language. Traditional printing language also cannot express alignment. What do we mean by that? Well, it means this kind of thing, where code with alignment has indentation that is sensitive to content in the preceding line. And this is to contrast with non-alignment, which is something that traditional printing language can express very well. And that is, it indents by a fixed amount of space, like 2 spaces. So that's traditional printing language. Let's now talk about the arbitrary choice printing language. It has an okay expressiveness. And that is because it can express layouts that differ in more than just white space. It can do that fine. It can also express alignment fine. But it has one downside, which is that it cannot express unaligned concatenation. And this requires some explanation. So ideally, we want to construct a document in a way that mirror the AST structure, right? So here I have return followed by the function call. And so ideally, I want to construct a document that is consisting of the document for return, the document for the function call, and the document for semicolon, and then I concatenate them together. But it turns out that in the arbitrary choice printing language, you do not have a construct to do this kind of concatenation. And so if you want to express something like this, you need to refactor your document in a significant way to make it possible, and that's not ideal. So that is why I say that the traditional printers has poor expressiveness, and why the arbitrary choice printers has okay expressiveness. So what do? We want good expressiveness. We want the best of both worlds. So we address this by creating a printing language that we call Sigma E. Sigma E, the goal is that it should be able to express all features from the traditional and arbitrary choice printing language. So that's the key idea. All right, the next bit is that we want to have good optimality objective. right? So again, let's try to learn from other printers. The traditional printers has poor optimality objective, and this might come as a surprise if you are familiar with the pretty printing literature, because they say differently, they say otherwise. If you read some papers, they will say that the traditional printers can output a layout that minimizes the number of lines, and it does not exceed the page width limit whenever possible. But that is wrong. Here's a counterexample. I can construct a document that encodes these two layouts. The left one does not exceed the page width limit and also has fewer lines. But the traditional printers will pick the right one. And this is due to how it employs a greedy algorithm to pick which layout to present to users. And greedy algorithm cannot look ahead into the future to determine the optimality. And so that's not ideal for our purpose. On the other hand, the arbitrary choice printers has an okay optimality objective. And that is because it does not suffer from this problem. It minimizes the number of lines whenever possible and avoids the overflow whenever possible. But it has one downside, which is that it errors when there is an unavoidable overflow, which again does occur in practice. For example, if you have a long string literal that you want to format, chances that it probably exceeds the page width limit, and it wouldn't be a good user experience to error. So that's why I say that the traditional printers has poor optimality objective, and why the arbitrary choice printers has okay optimality objective. So let's see, we want to have good optimality objective. We saw that the greedy algorithm is not what we want. And so what we will do is that we will formulate the problem as a dynamic programming task. And in order to deal with the overflow, right, we devise a concept that we call cost factory. This is going to be our optimality objective parameter. And it is a set of functions or values satisfying certain properties that the user can provide to you customize the optimality objective. I'm not going to go into detail for what these certain properties are, but if you are math nerds, this is, let me recall, totally ordered monoid with translational invariance, something. Here's an example of a cost factory. So you do not need to read this into detail, right? I just want to show you what it looked like. You can provide the types for the cost. You can customize that. You can say what the cost should be for each text placement. You can say what the cost for each new line should be. You can say how to combine the costs together. You can say which cost is less than the other cost. And this altogether can allow you to express some really good optimality objective, like trying to minimize sum of square overflow past the page width limit, and then minimize the number of lines. All right, the last bit is that we want to have a reasonable performance. I'm not going to talk about the great performance of the traditional printers, because that is accomplished by having a greedy algorithm, which, again, we already decided that we are not going to do. So let's see why the arbitrary choice printers has poor performance. Well, there are several reasons, but one reason is that the document in the arbitrary choice printing language can have a choice, and that creates the DAG structure, directed acyclic graph. For example, if I have this document on the right, it creates a choice between two ways to format X and Y, where X and Y can be arbitrary document. And if you write this down diagrammatically, it looks like that. X and Y are shared, they are reuses. But if you treat this document as a tree, like how you would normally do, then this DAG is unfolded, and the size of the DAG is doubled, right? And this is just only for one choice. If you have multiple choices, then the size of the DAG could be exponentially large compared to the size of the tree. And so to address this issue, we will do memoization by using the document identity. And to achieve the reasonable performance, we will use a data structure called Pareto frontier of low dimension to track the optimal layout. And the Pareto frontier of low dimension is really great because you can do operations like merging two Pareto frontiers together in a really efficient way. All right, so I'm not going to go into the rest due to the time limit. So let me just walk through real quick what else is in the paper. We have a survey of existing printers in the literature, and it is how I can come up with these counterexamples. We have details of our printing language, Sigma E. We have the printing algorithm for Pi E. We have functional correctness for Pi E. What does it mean for our printer to be correct? And that consists of two theorems, validity and optimality. And we prove this in the lean theorem prover. We have a time complexity analysis of Pi E. We have a formal framework to compare expressiveness power of printing languages. And this is going to tell what do we mean precisely when I talk about express features or express layouts, and what does it mean for a printing language to be more expressive than the other. I also implement Pi E concretely as a printer that is called pretty expressive. We have that in OCaml and Racket. And we evaluate pretty expressive against other pretty printers in and also in practical settings as a part of the Racket code formatter. And the result shows that it is competitive in the performance, and it is much prettier. So that's it. This is our pretty expressive pretty printer. These are the links for the full paper. Before I end the talk, though, I want to thank these people for making this talk possible. And yeah, I'd be happy to take any questions.
If you have questions for Oak, please step up to the microphone. And Oak, please unplug so we can get the next person set up.
Yep.
Well, I have one question. So I often find that I have code that mixes different languages. Maybe it's a string with some code inside of it, or maybe it's SQL like we saw in the previous talk. So do you have any tips for how to work around this problem? Or what does the Racket formatter do?
Well, I mean, one of the reasons why I want our printer to be expressive is precisely because the Racket language has like this #lang mechanism, right? That you can use arbitrary syntax. And so when I want to make a Racket code formatter, I wish for something expressive so that I can support all this stuff. Yeah. So
okay. Question?
Hi, great talk, thank you. I was wondering, I mean, people have fairly strong opinions about how their code is supposed to be formatted. So I was wondering, you know, how much you can kind of have the person writing a formatter using your framework to kind of, you know, tweak these little tiny things that people sometimes care about, or is like a lot of it is like controlled by these optimality functions and kind of more automatically chosen what's optimal layout. It's like, what's the trade-off here, I guess, what I'm asking.
Yeah, right. So if I understand correctly what you asked, so there are kind of like ways to control what gets output, right? One way is that you express it in the in the document itself, and the other way is adjusting the optimality objective and something like that. So I mean, it's a trade-off, and you need to. I guess you could just the help from both of them. Yeah.
So I guess what I'm trying to ask is, if you are like you have really strong opinions, can you make those opinions? Can make the framework understand exactly what you want?
Okay. So sorry, I think I better understand your question now. So this talk is mostly about a pretty printer, right? It does not talk about like, you know, which style you prefer. That would be more about the code formatter software. And I mean, I don't have opinion on that, but like you can be opinionated. Yeah.
Thank you so much.
Yep.
It's a yes. Okay, thanks again, Oak. Okay, and next up, Lisa is going to tell us how domain experts use an embedded DSL.
Great. Can people hear me okay? I tend to be really loud, so I don't want to like, okay, cool. Great. Okay, so hi, I'm Lisa Reynolds. I'm a PhD candidate at the University of California, Berkeley. And today I'm going to present some work done jointly with Professor Sarah Chasins in the Plate Lab. I'm also, actually my home department is the Energy and Resources Group at Berkeley, so I work between that department working on climate change policy and the computer science department. So I wear a lot of hats, and this project was cool because I got to put both the hats on, which rarely happens. So yeah, hope you enjoy. So I'm going to talk about introduction and motivation, then research questions and methods, findings and design implications, and a quick conclusion. Bear with me on the first part. It'll be a little long just because I want to make sure I set things up properly. Some things will be familiar, but others might not be. So the beginning is probably familiar. Experts across a diverse range of fields have come to rely on programming and computation, and in particular, I've noticed this in the earth sciences and climate change communities. So there have been various efforts that I've seen at universities that I've been affiliated with or working with, including Berkeley, MIT, and the JuliaCon community, where this is becoming prevalent. So these applications for domain-specific languages and programming tools for the earth sciences community and the climate change community. That's both researchers, but also policymakers. And in these situations, the practitioners often lack formal computer science training, but share problem formulations and vocabulary. So I say formal here because especially with the newer generation, we're often seeing that everyone's using programming or using it as a tool, but they lack formal training. And this is a slightly different audience with different needs than maybe people that we're used to designing tools for. So domain-specific languages are a long-standing and popular strategy for meeting the needs of such domain experts, and this includes embedded DSLs, which is what I'll focus on today. A brief pause for terminology. So I'm going to use the terms developer or designer to talk about individuals designing and implementing languages, and then user, end user, as the person using the language. This is a user study implementing some human-computer interaction methodologies. So user experience will be a broad term that I use to discuss many aspects of the programmer's interactions with languages. Usability, a more specific term about a programmer's ability to accomplish a particular goal. So briefly, the tool that I'm going to be talking about is called Mimi. This is a tool I've been working on for the past 6 years with my PhD advisor and a small team at UC Berkeley. It's a framework and platform to build a type of model called integrated assessment models. Happy to talk a lot about these with anyone who's interested, but for now, just know that they're a key type of model in the macroeconomic literature and policymaking communities that look at how climate change impacts the economy and then are used to underlie policy. Briefly, they matter, and this tool has actually been picked up, which has been a really great success. So one of our favorite things is the panel on the right shows that the list of models is now getting completely unwieldy for one PowerPoint slide. It didn't used to be this unwieldy, so that's really good. In the middle, you can see that a lot of universities throughout the United States and outside of the United States are starting to lean on this platform for academic research and publications, including our recent work in Nature. And we also collaborate quite a bit with agencies like the Environmental Protection Agency and the state of New York. So this work is also underpinning regulatory analysis and policy analysis. And then here, just showing that it's also underpinning actual federal rulemaking that's happening. So this is a snapshot of the public GitHub of the EPA. And this tool is underlying the social cost of greenhouse gases work that is a proposed rule on the docket right now. So I'm just going to stay like a couple key pieces about Mimi, just so for some context, but I can also go into more later. One is that these models are mostly modular, so we use sort of this Lego approach. People's mental mapping of these models is often their components linked together. So you have the climate system as a component, you have several pieces of the macroeconomy or components, and these are linked together, doing equations, producing variables. These are parameters for other components. So we use sort of a vocabulary that evokes that. So we have components, we have parameters, we connect with parameters. So that's kind of like the general structure that you see on the left. Or I guess it's your right. We interact a bunch with the package management system of Julia. This becomes important for user experience. I won't go into that a lot, but it is in the paper. And a lot of these models are represented as packages themselves, which ended up having a lot of implications, unexpected implications for users. We depend heavily on custom types and multiple dispatch. This is a big feature in Julia. So for example, here, model is a custom type here, and then we create a method to extend Julia's base run function to run a model. So again, we're sort of embedding using extending and using multiple dispatch. And finally, we're pretty macro heavy. I'm not going to talk about this a bunch in this particular talk, but I think it was an important finding that we had, the pros and cons, some of which are probably very familiar to folks. But we do use a lot of macros to define our types, such as components. All right, last motivation slide. Evidence suggests an opportunity for language designers to improve user experience via a better understanding of EDSL user needs. So while we noticed in the literature a lot of design tenets and a lot of descriptions about why embedding a domain-specific language as opposed to other implementation strategies is attractive for designers, but also that there seems to be a lack of usability. So for example, in this study, and I can go into this study later, but very broadly, the ranking for implementation effort on the part of the designer was #1, so designers seem to really like using embedding as an approach, but the ranking for an end user effort, which is a combination of quantitative and qualitative metrics in this paper, ranked nearly last. So this dichotomy seemed to present sort of an opportunity to understand a bit more about why this is happening and see if we can improve. So this will be brief. We designed our study around 2 primary research questions. The first is, what kinds of programming challenges do domain experts face during use of an EDSL designed for their domain? And the second is, which of these challenges arises specifically because the DSL is embedded or because of interactions between the DSL and the host? This latter part is partially because it's embedded, so there's interactions between a host. I'm not going to talk too much about the methods here, but I do want to emphasize that this was a user study with domain experts. So these are profiles of a few of the domain experts that we worked with for this study. They primarily came from non-governmental organizations, nonprofits, academia, and the federal government, all of them use programming in their day-to-day, but are not expert programmers by any means. Often we're picking up programming specifically for these tasks. And they do have a very common language and common experiences in the climate and economics domains. Okay, so I'm going to just talk about a few findings and design implications. I'd recommend you look at the paper if you're interested, because there are way more than I can describe here. But I'll describe a few findings meaning kind of the things we observe without trying to infer or speculate too much, and then design implications, the things that we think this might imply for language designers. We have 5 key categories of findings in the paper listed here. Impacts of host language, impacts of interactions between host and embedded language, engaging with EDSL-specific communities, engaging with EDSL-specific tutorials and code bases, and integrating multiple tools via the host language. And I'm just going to go into a few findings here. But in the paper, we try to frame this also as things that we find that sort of back up common tenets that we read about in the design literature, and also places where we actually find contrasting information, where we might want to rethink common tenets, especially in light of the idea of a new type of audience using these tools. So the first one is that we found some interesting results from blurring the line between the EDSL and the host language. So a lot of the common tenets, design tenets that we read, basically say you should make the embedded domain-specific language blur with the host language such that the user doesn't really know which one they're using at any given time. This makes a lot of sense for an experienced user of a general programming language. They can bring along their intuition with debugging, their intuition with syntax, to use the embedded language. And so I think there are a lot of advantages, but we also found a couple places where I think this actually introduced pain points, especially for novice users who are learning both the embedded language and the general purpose language at the same time, which was a bit surprising given the common advice. So I'll just do 2 cases. The first one here is where the integration was quite seamless. It seems minor, but this is actually really tough for new users, is trying to figure out where to look for help. So this is just an example where parameter is a custom Mimi type, but the user thought it was a Julia type. So they're trying to use the Julia help REPL to search for information. they see that it's not defined. I think eventually they went and looked at the Mimi documentation, but this contrast of where to look for documentation created some confusion and also just curiosity. Folks kind of wanted to understand what was Mimi, what was Julia. The second example is a bit more convoluted. This is all happening within a macro, which is important. But this is kind of where we imperfectly integrated. So this first line, temperature equals parameter with arguments, this is again within a macro, so this is going to be used by our parsing logic to generate code that will then be executed at runtime. This user was using a Julia formatter. So the Julia formatter put a semicolon at the beginning of this argument list, because in Julia you can put a semicolon between your named and unnamed arguments. So we purposely made this look so much like a function in Julia that the formatter picked it up and added this semicolon. But we didn't write our parsing logic within the macro to handle that semicolon, which sounds really minor, but you end up with this fairly ridiculous error message that the user cannot understand at all. Error messages is a whole other part of this paper. But this was a place where we kind of tried to be tricky and elegant and make it look like Julia code and actually kind of backfired on us. My advisor has a whole thing about how they shouldn't format within macros, so he and that guy are having a conversation apparently, but you know. He says it's a formatter problem, I think it's our language problem, but either way, this created some confusion. So just some design considerations. Again, there were a bunch of different findings in this general category. I just talked about one. And some of the things we concluded here, that it might be good to anticipate confusion for novice users and also expect some curiosity about distinctions. It might be good to pair documentation. And also sometimes explicit differentiation might be helpful. So even though it's a bit more clunky, a little less elegant, it might actually be helpful, especially for novice users. So two more kind of high-level findings. Some of these might sound familiar, but we still thought they were interesting. First, we found that users really wanted to engage with EDSL-specific communities. So we kind of combed forums. We saw very little question on Stack Overflow, on the Julia language discourse. It is a small user base, but still we found that basically all of them are engaging with the Mimi forum that we run or contacting us personally. Very few people are going to these general purpose language forums. They also reported that EDSL-specific support in these forums and seeing this community played a big role in adoption. So one user, for example, basically said that noticing that the research community was starting to use this tool at a workshop we ran was the main reason that he started using it. Because he's a PhD student, he's hoping to get involved with existing research, so he started using the tool. So implications for us here are that running this forum, even though it's a lot of work, is really valuable. And also hosting conference workshops and things to help bring the community together are really important aspects to designing this language. More broadly, it shows that perhaps EDSL designers don't get to just piggyback on the host language to use their forums and their documentation. We actually do have to kind of replicate it to create a community, which places extra burden on the designers and is an interesting kind of conversation, especially with open source software. And a final point is engaging with EDSL-specific tutorials and code bases. So one thing we noticed is that rather than starting new programs from scratch, participants tended to start from existing programs, either from other users or from the tutorials. So this is sort of that blank page syndrome. So we see here a model that already existed. This is a snapshot from a paper. This is a model that existed in the literature. And the authors of these papers used Mimi to add the blue section to the model. And this is a very common way that these models evolve in this literature. They sort of get like built onto each other and then new insights are gathered. Similarly, we saw engagement with EDSL-specific tutorials and code bases. So this is a case where I was lazy and it backfired. So I wrote this documentation. I'm writing a tutorial, and I decided to write this sort of everything but the kitchen sink tutorial. So I wrote this tutorial. It's basically a Monte Carlo simulation. I'm showing all these different ways that you can assign a distribution to a random variable. But this is not actually a program someone would want to use because I have a couple extra lines up here that don't end up getting used. So I assign a distribution to a random variable, but I never assign the random variable to an actual variable in the model. And this ended up confusing like 2 or 3 participants because they notice this, they don't understand why. Some of them figure out that it's useless code, some of them think they're doing something wrong. So the conclusion here is just to expect, basically, that users are going not to work from scratch, but work from each other's code or work from the code that you provide. One conclusion there is that we might be able to support this more by including EDSL features that allow users to build on each other's work, so we've been doing that. And also just to expect that this is going to happen, and that might have implications, for example, for how quickly we evolve the API, for how much attention we pay to the code that we kind of put out into the universe that people might build on, and also just kind of a humbling experience of realizing how much control or lack thereof we might have of the code that begins to get propagated and used. And the last thing is just that we speculate a bit about the connection to this particular domain. So climate change and climate economics are highly politicized, and just people are very worried about getting things right. So they tend to build on published work in incremental ways. And so more broadly, a conclusion there is just working on these domain-specific languages, paying a lot of attention to maybe the specific needs of that domain community would have helped us think a little bit more carefully about the implications. So that's all I have. Here's my email, and my email's number. Our website's up here, and the email is connected. Happy to answer questions. And I guess this is like the thing that people do too. I am also on the job market. So if people are interested, let me know. This is kind of interdisciplinary work that I don't know who has departments where it's interesting, but postdocs, anything, happy to chat. All right.
Hi, Michael Koblenz, UC San Diego. Thanks for the talk and thanks for the work. So I've started talking to a variety of scientists about programming things. And what I hear from a lot of them is Python, 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 Fortran, Python, right? And so you're somebody who has designed something that has gotten adopted. And so I'm wondering what tips you have or what lessons you've learned about how to build things that they actually appreciate and use. You mentioned some community things. I'm wondering what else you can talk about.
Yeah, and sorry, did you say you were talking to a specific field of scientists? I just didn't hear.
A variety of some oceanographers, some climate change people, a variety of different kinds of people.
Scientists.
Yes, natural scientists, yeah.
Yeah, well, one thing maybe we can chat after. There's a really great paper by someone who did like an ethnographic study at a climate group at the UK that has like some really good information. Maybe you've seen it already. Yes. But yeah, I think that the community building has been really important and the outreach, and I think we also just had to be very patient and sow the seed. So I think one thing that really helped was we got it into use in the federal government, which can be hard, but we got an NSF grant that paired with them and then helped them start using it. And now that researchers are seeing that the policymakers that they want to work with are using it, you're seeing a lot of impetus there. So I think linking it to policy helps a lot.
Okay, you two definitely need to talk more afterwards. One more quick question.
Yeah, very short one. To embed the DSL was one of the design decisions made. Another would have been to add additional models and aggregate the languages then afterwards. Did you also look into this as one of the approaches that could have been helped for not blurring up the models and
you mean
confusing here?
Designing a brand new language? Is that the question?
And put it besides the existing language, the models.
Sorry, I don't know if I... So the question is, why did we decide to do an embedded language instead of build a brand new one? Yeah, good question. Wasn't my initial choice, so I should first ask my advisor. But I think that the high-level answer was the low effort. So this is not our primary work. At this point, we're not even funded to do it. It's like a project. So I think it was basically, my advisor's a Julia designer, and so we could piggyback on top, and that kind of allowed us to keep it going.
Okay, thank you.
All right, let's thank the speaker. Now, Anders will tell us about Sagittarius.
Hi, I'm Anders, and me and my collaborators wrote Sagittarius, which is a DSL for specifying grammatical domains. So first, I want to talk about grammar induction. Grammar induction is where you learn a grammar, and it is a very, very, very old problem. It started in the 60s, so it's been over 50 years, if I do my math correctly, where Gold asked and defined, what is grammar induction? And then some years later, Englund, who's kind of the heavy hitter in grammar induction, started asking questions like, oh, how fast can we do this? And then came up with her famous L-star algorithm. And then there's been some follow-up work that does things like probabilistic induction. They discovered some limitations. There was eventually ad hoc format induction in the PADS project. And then since 2008, there's been a lot of recent cool work on using grammar induction for things like fuzzing, for things like profiles, a lot of really cool work. But it's got a long and storied history, and that is because grammar induction is very, very hard. Grammar induction is not the sort of thing where you have a couple papers and you solve it and then you're done. So why is grammar induction hard? Well, first of all, given a set of examples, Englund found that it's NP complete to find if there is a DFA of size k. Okay, well, NP complete, who cares about that? But even then, let's say you want to find an exact grammar, and you have membership queries, and actually, unless you can break RSA cryptography, membership queries don't really help, and you often will require an exponential number of membership queries. Although I guess if you break RSA cryptography, there's bigger issues. And furthermore, in practice, inferring even something this simple, like just any letter repeated one or more time, takes 679 membership queries. And that also means 679 calls to find a KDFA. This is using L-star, by the way. So it's really hard in practice as well. And it should be hard. I actually think that grammar induction is one that if you kind of give some thought to it, it is actually really intuitive that it's so difficult, because the space of possible grammars is actually incredibly wide and non-deterministic. It's hard to think about coming up with the correct grammar when they're so loopy, you know, they can each call each other, things like that. It's not easy. So grammar induction is something that is, in my opinion, both, I guess, theoretically hard, practically hard, and intuitively hard. So hopefully I've convinced you that this problem is hard. So instead of addressing this problem, I'm just going to say, let's solve an easier one. And also, I would say that general grammar induction is kind of under-constrained. So my solution is to constrain the search space. So this is the general approach, is we're going to describe the search space with a DSL. We're going to contextualize the search space by giving explicit preferences. And lastly, we're going to induce the grammar using some combination of semi-ring parsing and max SMT. So to do this, I'm going to do an extended example on CSV induction. And you would think, okay, CSV induction, that's a kind of easy problem, right? Oh, let's look at this CSV. I could come up with that grammar. It's a number, a string, and then a number, and there's commas in between. It's just comma separated value, of course. And so I could write this. There it is. Look at that. I have generated the grammar for this. I've got some strings and numbers that I'm not going to define here. I've got 3 cells separated by separators in each row, and a table is just 1 or more rows with new lines between them. Okay, well, actually, it's a hard problem. Look at this as one example. You have, actually, if you look at it, it's not a comma-separated value. It's actually a semicolon-separated value. But also, if you look at it, you could imagine that if you were a automated system, you might actually think, yeah, this is a comma-separated value. Look, there's regular commas in between them. There's kind of 2 or 3 commas each time. So this kind of looks like a comma-separated value. So it's actually, in my opinion, a hard problem, even just kind of in a basic way, and it's made even more hard by the fact that real CSVs kind of stink. Namely, the delimiters are either commas, tabs, or semicolons. You might think, oh, that's not that hard. Well, actually, that's not true. You can have crazy delimiters. The quote characters are the quote characters, right? Nope, not true. The string delimiters are slashes, of course. No. And lastly, you'd think, well, at least they look like tables, right? CSVs have a fixed number of columns. Not even that is true. So CSVs are actually quite difficult, and they're so difficult that there has been prior research work on how to do this. This is in the context of this thing called CSV Wrangler and these Python sniffer libraries. This is the sort of thing that people are actively working on. So what can Sagittarius, which is our language, do? Well, we're going to say that you could do domain-specific grammar induction for free. Essentially, rather than code up all these custom little tools, Sagittarius will actually build a domain-specific grammar inducer for you. And this is really inspired by Cygus, which is where you kind of can describe the problem, and then in our case, a syntax-guided grammar induction engine will solve it for you. But before we describe the CSV metagrammar, and I'll do a whole, work through the grammar thing, or metagrammar thing, I'm going to give a quick slide of formalism, because I want to describe what are metagrammars. I would say that they are sets of grammars, because I'm trying to define a search space. I'm trying to define the set of possible valid grammars. So we have a denotational semantics, which turns metagrammars into sets of grammars. And if you described using a intermediary semantics that's indexed by a natural number k, and that's with kind of a big step style semantics, and it says if mg steps to g, that means that it kind of non-deterministically steps to a grammar of complexity, which I'm not going to describe in detail, k. And this will be useful in their algorithm eventually, and the actual semantics is just the union overall k of the things that are set to. Okay, so done with formalism, let's go into metagrammars. So for Sagittarius metagrammars, we're going to start with the problem of, hey, we want to figure out 3-column CSVs where the rows can be just numbers or strings, something kind of simple. Let's come up with a metagrammar for it. Well, you know what? I'm just going to say at the start, let's just start with our grammar. And this is one of our design decisions for Sagittarius, is that we look like grammars. So actually, this grammar that I've written is indeed also a metagrammar. But there's an issue. This is a grammar that accepts 3-column CSVs right like this, where it goes number, string, number, but I might want to do something like number, number, string. That can't be handled here. So we need some sort of a way of kind of describing, obviously, multiple grammars. This is done with optional productions, which is expressed using these question marks. We could say that each cell goes to either, or the cell 0 can have a production to number, and it can also have a production to string. So we add these in, so now I say that cell 0 can go to number or string, cell 1 can do the same, and then I'm also going to do a similar thing for separators to say, yeah, maybe we can have any of these 4 separators. Okay, that's kind of nice, but this is a little heavy syntax, so I'm going to combine all these cell 0, 1, 2s into just a cell I, where I ranges from 0 to 2, and then I've kind of expressed multiple grammars in this in a terse way, just to make things a little easier. But there's an issue here. This option parameter, these kind of these optional productions, this is not like a choice type of operator. It's essentially saying cell can go to, and then I can have a production to number, and I could potentially have a production to string. So I could have, in this metagrammar, I'm allowing cell to go to nothing. I could choose to not include both productions. I could include just number or just string, and I could have a production for both number and string. Now, I'd say that, to me, in a CSV, I want to really have kind of well-defined data types, so I'm going to say that each cell can either step to a number or a string. So what I want to do is I want to constrain this. I do this with constraints. I'm going to add in this little constraint that says that the productions of each cell I is going to be equal to 1. So I'm just saying, yeah, we can only have 1 production for each cell I, which then just constrains the search space to be exactly either number or string. And I should also do this for separator, although I didn't include it for space on the slide. Oh. Okay, so now I want to step it up a level. We're not doing 3-column CSVs, we're doing n-column CSVs. The format should be largely the same. We've got these cell i's. Instead of I ranging from 0 to 2, I'm having I be a natural number. And we have some complexity to describe rows, but you can really think of this as being rows of some given length. And then the table of that given length, that width of the column, is equal to the the table of that length should be equal to the rows any number of times. So we start with the table, and we ask, okay, well, what should we give to the table? You'd think, oh, it should be table of some number. I don't know what number that is. So what we need to do is we need to introduce a new construct, which is existential variables. So I can say there is some row length, which is a natural number, and you start at a table of that row length. Okay, so I've made that change. Now I have this existential, so we can say, oh, it can be kind of this arbitrary fixed row length, and we've now actually described the full space of n-column CSVs in this kind of idealized CSV. We have a little bit of complexity. We would like to generally prefer numbers because kind of number or strings kind of include numbers as well as other stuff. So I want to use numbers by default, so I'm going to add in preferences where I can say, hey, I prefer using this number. Pretty nice. And then we're done. Okay, great. Now we know how to describe a metagrammar. Now we want to do the other side. We want to do grammar induction. So how do we induce from a metagrammar? We have this high-level algorithm, which is we start at complexity 0. We search for the best grammar G such that the metagrammar steps with complexity K to G. If a grammar's found, we return it, we're done. Otherwise, just increment the complexity and continue. So what's the hard part here? The hard part is figuring this best grammar. So this is our induce with metagrammar and K and our positive and negative examples. So how do we do this? Well, what we do is we take this metagrammar and we kind of explode it out into this giant grammar that kind of includes all of the possible grammars in the metagrammar. It's just this huge union, as well as some preferences and the constraints. So we do this extraction. Then we use this giant generated grammar, and we do a semi-ring parsing algorithm on the positive examples. The semi-ring parsing algorithm will extract a formula that describes the necessary rules, and we do the same for the negative examples, although we will take the negation of the formula because we don't want to include those necessary rules. And then we call maxSMT to find a model that will satisfy all these constraints that we've done, and then we reintegrate those constraints into the metagrammar to get an actual grammar. And we're done. So we have a theorem that if there is a grammar such that the grammar is in the metagrammar and the positive examples are in the language and the negative examples are not in the language, then we will find such a grammar. So yay, we're correct. Okay, well, so that's our full algorithm and our full, well, I didn't give all of the aspects of the DSL. Please read the paper if you're interested in more. But what about the evaluation? We wanted to test in the evaluation some core questions. Can we express a number of interesting metagrammars in Sagittarius? Are we fast enough to actually be useful? And can we enable better sample efficiency? Do we still need 690 some examples to generate easy grammars? So to answer the first question, we constructed a benchmark suite of a lot of metagrammars ranging from things like states to things like email addresses to SQL. And we also did 3 case studies on XML, CSV, and SQL. I thought these were really interesting. XML, we actually had this issue where the first time we built metagrammar, we kind of built it poorly, and we built it with in a way such that it had still a very wide search space. So what we did was we rewrote it a little bit, and we found that we could speed up synthesis a lot, kind of building up and agreeing with our intuition that more constrained search spaces are easier to search through. For CSV, well, we did this extended comparison, and we found, yeah, we have similar accuracy to prior tools, although we are slower than them because we're more general purpose. And then for SQL, this was kind of interesting because it was inspired by one of our collaborators who was in the industry and actually kind of had this issue where he needed to extract and find the dialects of various SQLs, and our tool, Sagittarius, was able to do that. Speed efficiency, we're pretty fast. We compared to ProSynth. The x-axis is time, y-axis is benchmarks completed. Higher is better. ProSynth is a logic programming engine, so it's not built for grammar induction, but we can use the logic programming to do grammar induction, so we kind of compared to this and this with a few added benefits, and we found that Sagittarius, which is obviously built for the domain, performs better, as you might expect. We compared the speed, and we found that definitely the most time is spent in parsing, so I would recommend everyone should build cool general semi-ring parsing algorithms. I really would like these to be sped up. This is where things could really be improved. And example efficiency, I don't have time to go into the details, but yeah, we're pretty sample efficient. So I would say for the core questions, we definitely succeeded on that. For fast enough to be useful, I think we can do a little bit better, and I think actually this algorithm can be done a little bit better with better parsing algorithms, and do metagrammars enable sample efficiency? Yes. Shameless promotion, I am hiring. Me and Yupong have started a relatively new PL group at SFU in Canada, so if you are interested in a PhD where you do synthesis, domain-specific languages, type systems, whatever, let me know. So yeah, I'm happy to take any questions.
Please step up to the mic with questions, and our next speaker will get set up now. Anders, actually, I had one question on the plot with parsing. It went by very quickly, but it looked like there was at least one case where parsing was not the bottleneck. Is that true? And what was happening there?
Okay, that was in XML, and this is actually a really interesting one. So I guess if many of you, or those of you who've worked with Max SMT, you might have experienced this. The SMT and finding a satisfying thing is actually blazing fast, can do it no problem. But Z3 can get a little, we use Z3, it can get a little bit hung up on really wanting to make sure that it has found the right and optimal allocation. So it'll find something. If we remove the max constraints, it finds it immediately, but it spends a very long time spinning and looking for better possible assignments.
Okay, thanks. More questions? Then all right, let's move right along and recover our lost time in the beginning.
Okay, so hello everyone. Oh. Okay, fine.
Okay, next up we'll hear about Matt 2 steps.
Hello, everyone. I'm Huanqi Cao from Tsinghua University, and I'm here to present our work on Mat2 Stencil, a modular metrics-based DSL for explicit and implicit metrics-free PDE solvers on structured grid. A long name, right? Our team is mostly background in the high-performance computing, so it might be not so professional from time to time, but bear with me. So first, let me get some background on the PD solvers, which starts from the stencil DSLs. There are already many of them implementing stencils targeting PDE solvers. In those languages, user can define stencils corresponding to discretized PDEs, which is usually a small weight grid, and applying such stencils onto a grid will get a weighted accumulation on the on each point's neighborhood, like in this equation. We can see that it reads the 5 points around xij and compute the yij. By applying those stencil operators, written down stencil DSL programs can compute the result grid in ampersand parallel and incurs no spatial dependence. Those computations serves explicit solvers well, but not for the implicit ones. We denote such computation as Jacobi-style stencil and following the Jacobi iteration algorithm. Unlike explicit solvers, only requiring applying those stencils, implicit schemes, that's a kind of time scheme, when executed on structured grid, they require solving linear systems. So we can see here that in implicit solvers, it needs to solve A applied on X equals B, in which we can see that the application is actually linear, so it becomes a linear system, linear problem to solve. The solving can be achieved through direct methods and iterative methods, both of which will require spatial dependence, like it needs to first solve x minus 1j and then get the xij to be determined. So we notice this kind of stencil operations as pseudo style since it's still stencils given it operates on the neighborhood, but it has the special dependencies that reflect the structure of the Gauss-Seidel iterations and more algorithms. But this kind of stencil operations is not yet addressed by existing stencil DSLs. So another direction looking at the problem is to see the stencils as sparse matrices. It works for both explicit and implicit solvers, in which we can see the 1D case of stencil A applied on X is equivalent to applying a sparse matrix multiplication. And so in this abstraction, the steps taking an implicit solver will be first construct the sparse matrix to be stored in memory like in CSR or ELL format, and then calling the third-party libraries to compute the different sparse linear algebra routines. So we here have two kind of methods here, one being matrix-based and the other being matrix-free. So the matrix-based method is useful in the implicit solvers, but is slow due to lack of structure in the library implementation, and it's hard to program since the matrix construction for complicated problems can be twisted. On the other hand, matrix-free approaches, mostly the stencil DSLs, are fast and easy to programming, but only works for explicit solver. So the basic idea is to bring matrix-based abstraction to the matrix-free implementations, mostly over DSL. Up to here, we can start introducing our domain-specific language, which is met to stencil, turning matrices into stencils, either in explicit or implicit solver. The first thing to resolve is the matrix construction, in which we identify some basic matrices and enable arithmetic between them that helps constructing complex problems. For example, the DX matrix here is a discretized version of the par2 par x differential operator here. By using it, the equation below can be discretized easily into either explicit or implicit form. We can see that the first one is simply multiplication between matrix and vector, and the next one is to have requires to solve the linear system. And with this abstraction, we can show an ultimate example that in the next parallel benchmark, they need to solve 3 of the equations. They took pages to define the scalar form in their tech report, but in our DSL, we can write it down in merely 3 statements. And to describe the structured sparse matrices we mentioned above, we note that structured sparsity can be expressed as codes. In specific, mimicking the compressed sparse row format, which is widely used in the sparse linear algebra routines, we ask for a row function for each sparse matrix that it accepts a row index as a parameter and returns a list of non-zeros in a row, each of which is a pair of column index and matrix value. The example matrix here is just the above example, and it can be implemented as the right set. We can also enable row functions with various additional features. One is to allow it to have row index dependent control flows, and the other is to automatically derive row domain size from the column domain so that it's more general and can be applied to any sized, arbitrarily sized grids. Besides, we also support multidimensional domains and tensor type values for the structured sparse matrix, which we talked in detail in the paper, but we'll omit here. And then it's a comprehensive example here, Gauss Seidel iteration. It's an example of implementing the Seidel style routines in our language, and there's more of them, not just this one. But the core idea shares, since they all read and write to vectors according to sparse matrices in domain loops. And finally, M2S support a rich set of operations based on the row function abstraction. It can do iterative solving algorithms through invoking row functions in the domain loops, as just described. And it can also assemble new structured sparse matrices through wrapping row functions into new ones, so that we can multiply, adding, or subtraction between two sparse matrices. Thanks to all of that, we can program the various problem solver in about 5 times to 10 times shorter. And the next thing, it comes down to how we stage the code into matrix-free, since we use the type-based multi-stage programming. And it's very much like LMS, but we make it possible to overload the corresponding methods for the classes representing stage 2 symbols, making it customizable. So we then overload the domain objects to get its for loops staged into nested for loops, so that it's not generating the loop body at a compile time various times. And the idea to stage it out is actually splitting it into 2 stages. One is to compile it in Python, and the other is generated code on FreeTensor. FreeTensor is also a work by our co-author, so the staging process goes smoothly, except on this important and common pattern. Consider the code here. It manipulates stage 1 object non-zeros. And with regard to the stage 2 condition, I larger than 0, recalling that I is a stage 2 iteration variable. For such programs, human solution would to be discussed different cases, either I larger than 0 or not. So our solution follows. Whenever a condition failed to resolve it at compile time, we backtrack and discuss both possibility. The backtracking is accomplished through throwing an exception containing the condition expression, and then the domain loops handler, which is the overloaded for each method, it catches the exception, try twice, one assuming it's false and the other true, and finally wrap everything together into an if-then-else statement. Additionally, identifying the commonly overlapped condition expressions, we perform deduplication with the help of C3 so that the cases number won't explode. Finally, is our backend. It mainly involves our novel automatic parallelization method Sooth, which is based on the polyhedral dependence analysis and our newly came up strategy. So the point is that unlike the embarrassingly parallel Jacobi-style stencils, Seidel-style stencils are harder to parallelize. They have spatial dependence inside their nested loops. In this example, the written cell of X depends on the first, needs to be computed after the first terms on the right-hand side and must be earlier than the later 4. So existing auto-parallelism methods suffer from either high startup cost or bad locality. So we want to resolve this issue. Firstly, we retrieve the dependence graph from polyhedral analysis. This is expanded and actually is in symbolic form. Then we check the dependencies crossing the thread boundaries, in which the thread's tile size is determined by the grid size and thread number. And then notice I don't know if you can see that clear, but it's there's a red arrow here, and we can see that the 3 blue arrows dominate this one. So the red one is redundant, and we want to eliminate it. And eliminating such synchronizations, we get a compact set of synchronization to work with, and then we can do code generation on the result. So the whole thing is automatically analyzed and generated to the code which is parallelized with OpenMP. And as a result, our system is able to run on a commodity server, a single commodity server with comparable performance to the manually optimized implementation. So that's all. Thank you.
Okay, step up with questions, please. I was curious if you're familiar with Phoenix.
I'm sorry?
Phoenix, which is a language that takes Python-like code and then compiles it down to finite element and finite volume solvers for PDEs. And how would you relate your work to that? Would this be another backend, possibly, for Phoenix?
I don't really heard about it.
Okay.
I'm sorry.
And then, okay, a related question to that is, what surface language would you imagine a programmer would use for interacting with mat to stencil? Is the language that you showed the surface language, or would you imagine compiling down from something else to that?
Our front-end language is embedded in Python, and we compile down to first FreeTensor IR, and then it's down to C, and gets compiled by GCC. So.
Okay, excellent.
Thank you.
Other questions? And let's thank the speaker. Okay, and now for our last talk of the session, we will hear about a verified implementation of SQL. It's good here. Okay.
Hello, everyone. So I'm going to talk about one of the most famous DSL, which is SQL, and how to compile it to imperative code. So we built a certified compiler that takes a SQL select query in a large subset of SQL and produces imperative code with a JSON data model. And this compiler, as I said, is certified in using the Cockproof Assistant. We also provide a backend which produces JavaScript code together with a runtime in order to be able to execute this code. This backend is not certified. So you may wonder why we want to certify something about SQL, since it's a very simple language that we teach to undergrad students. Actually, I have one example of something which may be unintuitive in SQL. So in this example, we have two relations, R and S. We only have one attribute of type integer. In R, there are two values, 1 and null, and in S, only one value, which is null. And we look at this query, which selects basically the elements from R, which are not in S. So I don't have time for you to think about the result, so I'm going to give it right now. We may think that 1 is not in S, okay, so it should be in the result, but actually the result is empty. Because when we try to see if 1 is different from null, the answer is not yes, the answer is unknown. Okay, we don't know if 1 is different from null, so we are not going to put it in the result. And similarly, when we ask if null is different from null, the answer is also unknown, so it won't be in the result. So this is one example of the difficulties that may arise in SQL. And actually, it's non-trivial to build a correct compiler for SQL. We made some experiments, and in one of the experiments, we used AlaSQL, which is a SQL interpreter in JavaScript, which is quite used since it has many stars on GitHub. And actually, it doesn't give the correct answer for this query. So we reported the bug almost 2 years ago. There are 4 people working on it, but it's still open because it appears to be very difficult to implement correctly nulls in SQL. So actually, instead of calling this language SQL, it may have been called SQL, because it's a language with a very subtle semantic, even for common features. So I talked about null and onion values. You may think that you never use null, but actually it appears everywhere, since lots of databases come from spreadsheets. And if you have an empty cell in a spreadsheet, it's going to be a null value in the database. Another major difficulty of SQL is correlated queries. So I'm not going to talk about it because I don't have time, but it raises scoping issues. So our main result is a certified compiler from a large subset of SQL which endorses nulls and correlated queries to an imperative language. So it's designed for in-memory database. Okay, it produces code that can be embedded into this language. And we also have certified query optimizations in the middle of the process. And we also provide, as I said, the JavaScript output and runtime in order to be able to run it. So I'm going to present in more details this compiler, but first I will show it on an example. So I take the same query that I've shown before. It's written in SQL. The first step of the compiler is to go to a language that we call SQL Coq, which is a Coq representation of SQL queries. And this step is simply decorating the query by giving names, explicit names to everything. So for instance, here we have from R. In SQL Coq, we force this R to give a new name. So we will say now this table is called T0 and the attribute is called X. Okay? And so on. So the same for table S. And then we have to put a bit more select on top of them in order to recover the names. But it's simply naming decorations. The next step is quite standard. It's going to relational algebra. So in this query, here, for instance, the internal from table R T0X is going to be this pi in the middle, and so on. The where clause is going to be a selection, and we have the top projection corresponding to this select. So why do I call it SQL alg and not simply algebra? It's because it's actually an extension of the relational algebra in order to encompass SQL specific aspects like aggregates or null values. Then I'm going to simplify the examples and take only a very small part of it because otherwise it's going to be very huge on the slide. So I take only the internal projection. The next language is a nested relational algebra. So it's a language in which you can have tables of tables, okay? And in this case, the projection is simply going to become a map. So chi is a map operation on a table, and you can iterate. For instance, here you iterate the fact that you project on one attribute. And finally, and in this language, there are many query optimizations that are possible, so they are already implemented. So in this example, there is nothing to optimize, but we can run these optimizations if we want. And finally, we go to an imperative language. So in this query becomes a function that takes a database. So the blue part of the result is something which is always present. Okay, it's a function that takes a database. You give names to the tables that are in the database, and you create a new variable ret, which is going to be returned in the end. And in the meanwhile, the black part it corresponds to the actual query and puts the result into red. So this works. This is the main picture of the compiler on an example. It's actually based on two previous works. The first one is the compiler from SQL-Coq to SQL-Alg, which has been designed in order to have a very precise semantics of SQLs with nulls and correlated queries. And the second work is the nested relational algebra with optimizations and with the compilation to another language, which I'm going to detail later. So these two works were already existing, and what we do is to bridge the gap between them, and also to bridge the gap with standard SQL and a backend language. So our first contribution, I'm not going to say much about it, is embedding the translation between SQL and SQL-Coq. As I said, it's not difficult, and it's also defined as a Coq plugin, so it can be run outside Coq and inside Coq. The two contributions I'm going to talk about is the bridge between SQL algebra and nested relational algebra and the backend. So let's start with the first major contribution. So, as I said, the SQL-Alg is an extension of relational algebra with things that you find in SQL like grouping, aggregates, null values, and so on. And the NRA is a nested relational algebra, which doesn't know anything about nulls or correlations and so on. Okay, so I show some examples of the difficulties that may appear in this part. So we have seen that projection is mapped to is translated to a map. So this is quite standard. But if we look, for instance, at filters, it's not just translated as a filter. So here, the formula phi, big phi is translated as small phi. The internal query Q is translated as small q. But we have to add something here to reflect the fact that the scope is going to change. Okay, I won't have time to enter into the details. Another example, if now we know that the formula phi is y equals x, for instance, then the translation of this formula is not just y equals x. It's actually a bunch of things to reflect the fact that y or x may be null values, and so the equality may return unknown. So we go into three-value logic, for instance, that is reflected by the fact that we have left to represent value, actual values, and right to represent unknown values. So that's one difficulty. A second difficulty is to go from a stratified queries to nested queries. So in nested relational algebra, everything is at the same level, okay? And whereas in SQL, we have the main queries, which contains formulas, which contains expressions, and so on. So we had to reflect the fact that we have a stratification on one side, but only one thing on the other side. So it makes complex here the functions that translate to an array and the theorems to prove that these functions are correct, which needs to be really intricated. So to sum up the challenges, I've presented two of them, the SQL subtleties, the fact that we go from stratified to nested. Two other challenges that we made is the fact that in SQL-Alg is defined with two layers, an abstract layer in which everything, we don't know how data and so on are represented, and the concrete layer, which is the executable part. So we had to cope with this and to first prove something in the abstract level and then make them concrete. And the other challenge is that this translation produces overhead. As I've shown here, you see that it becomes a very big formula, right? So we had to make sure that we don't have too much overhead. And actually, Coq is not just something to write proofs and then you are happy. It's a very nice tool to help in the design of the proofs. Because using it, we were able first to work at the level of specification and then implement the system with concrete objects. The second major contribution is from the nested relational algebra to an imperative language. So I'm going to give a bit of details about this. So it's also a compilation chain whose first step was already present in the original paper. So let me give a bit of details about all the languages. So we first go to a name-nested relational calculus. So I didn't say it, but in nested relational algebra, everything is defined using combinators instead of variables. So in NNRC, we are going to explicit variables and environments. That's the first step. The second step is to replace expressions with statements. Okay, you can see NNRC as a functional language with expressions, and we go to a more imperative language in which we have statements and return value. Then we go to another language in which we have only one single namespace. Okay, in the previous language we had multiple variable namespace to separate things. And now we go to a single namespace language, which implies to remove possible shadowing between variables. Finally, we go to our imperative language. So the last functional feature that was remaining is pattern matching. So we remove pattern matching and replace it with conditional statements. But it's not the final step, because in all this chain, the data model is abstract, so it means that we can plug any data representation that we want. And this is the last step. We choose to implement a JSON data representation. So we use collection and records to represent, so we switch from collection and record, abstract collections and records to JSON. So in this work, in this part, the challenges, the first one I already said was to separate problems. Okay, we don't want to translate everything in one step. So we want to go first from functional to imperatives and to look at variables and so on. And the second challenge is the same as before. It may have overhead to do all this, but in this case, we made some preliminary experiments, and it shows that we have limited overhead. So to sum up the takeaway message, I hope I have convinced you that data management languages, and in particular SQL, are hard, so they require strong guarantees. And what we do in this work is to provide a certified compiler designed for in-memory databases. And it involves a translation from SQL to an optimizing algebra, which is non-trivial, and a combination of proof techniques that we used in the code proof assistant. Our perspective, short-term perspective, are to add optimization in an error half in order to remove the overhead that was created by the translation from the relational algebra to the nested algebra, and to give to perform more benchmarks to concretely measure this overhead. So everything is open source and available online if you want to try it, and you can find more details in the paper, which, be careful, was published at UPSLA last year, not this year. Thank you.
Hello, this is Amir from the University of Edinburgh. So I have actually two questions. So I think one of the questions was kind of hidden somewhere. So you're using back semantics, not set semantics. Am I right?
Yes, it's back semantics.
Okay. The second question is that at which stage are you introducing hash table data structure? Because in nested relational algebra or nested relational calculus, you don't have explicit joins. So you have like nested loops, which are bad in terms of performance. So at any point of your pipeline, do you introduce the notion of hash tables to implement hash joins?
So no, we actually stay at we never go towards the nested loops and so on. So we stay at the level of algebra, and then we go to the imperative language, but we don't go to this lower parts that can be in which SQL can be computed.
Okay, yeah, because in comparison with then in-memory databases, if you don't implement hash join, the performance is going to be very bad. If you're
the idea is to produce codes that can be embedded and can be used in a programming language. So, for instance, we have a JavaScript backend, so you can directly run it in JavaScript if you want.
Okay.
It's it's another way to prove what you said. Yes.
Okay. Thank you.
Thanks.
Okay, so this ends our session, and it ends the first day of UPSLA. Let's thank our speakers again.